Welcome to a quiet place for reflection, where curiosity can move slowly and large ideas have the space to unfold without pressure. Wherever you find yourself tonight, whether the room is already dark or the evening is just beginning to settle, I am glad we can share this time. This is a space designed for letting go, for allowing your thoughts to soften their focus while the gentle current of science flows in the background, like a quiet voice that asks for nothing in return. Tonight, our thoughts will drift toward a question that sounds immense when spoken aloud, but one we can approach without feeling overwhelmed. We will be exploring the true scale of the observable universe. This will not be a journey of sharp turns or sudden revelations, but rather a slow and careful unfolding, letting the sheer size of it all reveal itself one layer at a time, much like how your eyes gradually adjust to the darkness when you step outside to gaze at the stars. For many, the very word universe can trigger a sense of profound disorientation, summoning numbers too vast to visualize and distances that seem to defy language. It can feel like attempting to grasp the quantity of sand on every shore on Earth, then multiplying it by a concept for which we have no name. The observable universe, however, is a subtly different notion. It does not represent the entirety of existence, nor does it make a definitive claim about the ultimate scope of reality. It is, quite simply, the portion of the cosmos from which light has had sufficient time to travel to us since the beginning of all things. That distinction is significant, and we will return to it later. For now, it is enough to let that phrase rest for a moment. The observable universe. It describes a domain defined not by physical barriers or edges, but by the interplay of time, motion, and light. It is a sort of cosmic sphere centered precisely on you, regardless of who or where you are, for the simple reason that any act of observation must originate from the observer. Before we venture deeper into that concept, take a moment to acknowledge your own location right now. What is the time where you are listening? Perhaps it is late in the evening, or the early hours of the morning, or somewhere in between. The world outside your window might be still, or it may be alive with a gentle hum, unaware that you have briefly stepped into a much grander narrative. And whatever that place may be, on any continent and beneath any sky, it too is situated within the observable universe, carried along on the same cosmic currents as everything else. If you find this kind of unhurried exploration to be a source of comfort, or if you enjoy letting complex questions unravel at a pace that makes no demands on you, you are always welcome to like this recording or subscribe to the channel. Doing so helps this small harbor of calm find its way to others who might be seeking a gentle place to rest their minds. There is no urgency in that either. You can always return to it some other time. Now, rather than jumping directly into figures and measurements, it is often more helpful to begin with a familiar scene. Picture yourself standing outdoors on a clear night, far from the glare of city lights, where the sky is dark enough for the stars to truly emerge. As you look up, your attention is first drawn to the brightest points of light, perhaps a planet or two, and a few constellations you can name. As your vision adapts, more and more stars begin to materialize. You see fainter ones, distant clusters, and a soft, hazy ribbon of light stretching across the heavens, which you come to recognize as our own Milky Way galaxy, viewed from within. This experience is itself a profound lesson in scale. What you are witnessing is not a flat canopy decorated with lights. It is an immense depth, with distance layered upon distance. Some of those stars are only a few dozen light years away, while others are thousands. And those faint patches that resemble soft clouds are not clouds at all, but entire galaxies, each containing billions of its own stars. Even with this magnificent view, you are seeing only a minuscule fraction of what is actually there. The vast majority of the observable universe remains invisible to your unaided eyes. This is not because it is absent, but because it is too distant, too dim, or emits light in wavelengths your eyes were not designed to perceive. Telescopes are what extend our reach. Radio dishes can listen for signals where our eyes see only blackness. Space observatories, drifting high above the distorting effects of the atmosphere, gather ancient light that has been traveling for billions of years on its journey to us. And that idea alone is worth pausing to consider. Light does not arrive instantaneously. It moves at a finite speed, incredibly fast by our daily standards, but not infinite. When you gaze at the moon, you are seeing it as it was just over a second ago. When you look toward the sun, you are seeing it as it existed approximately 8 minutes in the past. The stars that populate your night sky may no longer be precisely as they appear. Some may have changed, and some may even have ceased to exist, their final light still traversing the immense gulfs of space. Consequently, when we speak of the observable universe, we are also speaking of a view that is simultaneously a history. The farther we look into the cosmos, the deeper we are peering into the past. There is no way to separate distance from age. They are woven together by the constant speed of light. This is the fundamental reason the observable universe has a limit. It is not because there is nothing beyond that limit, nor is it because space itself comes to an end. It is because the universe has a finite age. There has only been a certain amount of time for light from the most distant objects to complete its journey to us since the beginning. Anything farther away than that threshold exists beyond our current observational horizon, not necessarily forever out of reach, but certainly beyond our sight for now. The phrase "edge of everything" can be a source of confusion here. It tends to suggest a distinct boundary you could point to, or a destination you might one day arrive at if you traveled far enough. But the edge of the observable universe is not a physical wall. It is better understood as the most distant sphere from which information has had time to reach us. It is a horizon, functioning in the same way the horizon on Earth marks the limit of your sight from your current position, even as you know the world continues on beyond it. As you let this idea settle, it is perfectly fine if the numbers do not yet feel concrete. They do not need to. The human mind did not evolve to intuitively grasp billions of years or trillions of kilometers. What is more important, especially in this quiet moment, is the overall shape of the narrative. The universe has been expanding, light has been traveling across it, and you are situated at the very center of your own observable universe, simply because the act of observation radiates outward from wherever you happen to be. That final point often catches people by surprise. At first, it can sound strangely self-important, as if the cosmos were arranged specifically around each one of us. But this is not a matter of significance, it is a matter of geometry. From any point in the cosmos, an observer would find themselves at the very heart of their own sphere of observable space, a domain bounded by the greatest distance that light has journeyed since the beginning of time. An individual in a galaxy billions of light years from our own would possess a unique observable universe, one that overlaps with ours in some areas, while extending into regions beyond our sight in others. This makes the question of the observable universe's size a quietly personal one, as the answer always depends on a specific location. It is a question posed from a particular here and now, from the place where you are listening, breathing, and allowing your thoughts to settle. For the moment, it is enough to simply rest with this starting point. You exist within a cosmos that has been unfolding for billions of years, carrying light over unimaginable expanses, silently creating the conditions for such questions to even arise. The term observable universe is more than a scientific definition. It serves as a quiet reminder of the inherent limits to our direct knowledge, and that even within these boundaries, there is more than enough wonder to fill the mind. When cosmologists employ the word observable, their usage is exceptionally precise, though this might not be immediately apparent. In common conversation, observable simply suggests something that can be seen or noticed. Yet in the context of cosmology, it holds a far more rigorous meaning, one that quietly establishes the absolute limits of everything we can ever hope to measure, photograph, or study directly about the cosmos. To truly grasp this concept, it helps to release the notion of the universe as a static entity sitting out there, entirely visible if only our telescopes were powerful enough. The universe does not behave like a fixed landscape waiting for a survey. A better analogy is a conversation that has been in progress for billions of years, where information moves at a finite speed and you can only ever perceive the parts that have had sufficient time to reach you. The ultimate speed limit for this information is set by light. Light is not merely illumination. It is the universe's primary courier of information. When an event occurs in the distant cosmos, a star ignites, a galaxy takes shape, a gas cloud collapses, our ability to know about it depends entirely on light, or another form of electromagnetic radiation, carrying the evidence of that event across space. And regardless of how sophisticated our technology becomes, that information can never arrive faster than the speed of light. This is where the concept of observable truly begins to crystallize. The observable universe is not delineated by the reach of our eyes or even our most advanced instruments. Its boundary is defined by the distance light has been able to travel since the universe first came into being. Anything that lies beyond that cosmic horizon may very well exist, but it has not yet had the time to send a signal to us. From an observational standpoint, it remains beyond our grasp. What this reveals is something profound. The observable universe is not the same as the entire universe. It is a subset, a specific region carved out not by any physical barrier, but by the passage of time itself. And this region continually expands as time moves forward, allowing light from ever more distant places to finally complete its journey to us. Imagine striking a bell in a vast, dark field. The sound wave propagates outward in every direction, but a person standing a great distance away would not hear it instantly. Until that sound reaches them, the event of the bell ringing has, from their perspective, effectively not yet happened. Light functions in a similar manner, though the timescales involved are not seconds, but millions and billions of years. This has a crucial consequence. Every observation is delayed. We are never seeing celestial objects as they are in this moment, but rather as they were when their light first began its journey toward us. That time delay increases with distance. We see nearby objects with only minor delays, while distant objects appear to us as they were deep in the cosmic past. At the most extreme distances, we are looking back toward the infancy of the universe itself. So, when cosmologists discuss observing the universe, they are, in essence, talking about interpreting a historical record written in light. The observable universe represents the portion of that record that has reached us to date. There is another layer of subtlety concealed within the word observable, and it relates to perspective. The observable universe is always centered on the observer. While this might seem counterintuitive at first, it is a direct result of the way light travels. No matter your location, light arrives from all directions at the same constant speed. This naturally places your position at the center of a sphere whose radius is the maximum distance light has traveled since the universe's beginning. If another observer were watching from a galaxy billions of light years away, they too would be at the center of their own observable universe. Their sphere would share many regions with ours, but it would also encompass areas we cannot see and exclude some that we can. There is no single, universal, observable universe that all observers share. There are as many observable universes as there are points of view. This does not imply that observation is subjective or arbitrary. The physical laws that govern it are consistent everywhere. The only thing that changes is the vantage point. Just as the horizon on Earth is determined by where you stand, the cosmic horizon is determined by your location in the universe. It is also important to clarify a common misunderstanding. The size of the observable universe is not a limitation imposed by the sensitivity of our instruments. Even if we could construct a perfect telescope, one capable of detecting a single photon from any distance, the observable universe would still possess a boundary. That boundary is established by time, not by technology. In fact, we are already capable of observing light that has been traveling for nearly the entire age of the cosmos. The most ancient light we can detect originates from an era when the universe was very young, long before the first stars and galaxies formed. That primordial light has been stretched and cooled by the expansion of space, but it still arrives today, marking the present-day edge of all that is observable. Beyond that edge, there could be more galaxies, more cosmic structures, and perhaps an unimaginably vast expanse of space. But without any information reaching us from those potential regions, science has no direct method to confirm or deny their existence. Observation ends where the flow of information ceases, even if reality itself continues on. Another key point is that observable does not necessarily mean visible in the conventional sense. A great deal of what we study in cosmology is invisible to the human eye. We observe the universe through radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Each of these is a form of light that carries information about different physical processes occurring across cosmic history. Therefore, when scientists create maps of the observable universe, they are not merely taking pictures. They are assembling vast data sets from many different wavelengths, each one revealing a unique chapter of the cosmic story. Hot gas glowing in X-rays, cold dust shining in infrared, and ancient radiation lingering as a faint microwave hum. When taken as a whole, these observations provide a layered perspective on the history of events within our cosmic horizon. The very word observable carries with it a sense of humility, an acknowledgement that our understanding is inherently limited. This isn't a limitation of our intellect or our endeavors, but rather a fundamental constraint imposed by the universe on any single vantage point in space and time. At first, this notion can be unsettling, as there's a profoundly human desire to see the complete picture, to possess the entire map. The universe, however, does not grant this to any observer. Each observer is situated within the cosmos, receiving information at a finite speed, and is perpetually enveloped by regions that lie beyond their view. In a way, there is also something quietly reassuring in this boundary. It suggests the universe is not a finished, static entity awaiting a complete inventory, but is instead a process that is continuously unfolding. With the passage of time, the observable universe expands as light from ever more distant sources arrives, making more of cosmic history available to us. At this very moment, light that began its journey from faraway galaxies billions of years ago is still traveling toward us. Observers in the distant future will perceive a different observable universe than we do, provided the cosmos remains transparent enough for that ancient light to complete its journey. Their cosmic horizon will encompass regions that are currently invisible to us. The expansion of the universe, of course, adds a layer of complexity to this picture, a topic we will explore more deeply later on. This expansion implies that not all light will ultimately reach our location. Some regions are receding from us so rapidly that their signals are lost to us forever. Yet even this reality is incorporated into the definition of what is observable at any specific moment. In the present, observable refers to anything whose signal has either already arrived or could, in principle, still arrive, taking into account the entire history of cosmic expansion. It is a dynamic boundary shaped by cosmic conditions rather than a static, unmoving wall. Another subtle but important point is that the act of observation does not necessitate a conscious observer. The universe is indifferent to whether or not it is being watched. When cosmologists use the term observable, they are indicating that information from a particular region has the potential to interact with detectors, instruments, or even just matter at our location. Whether anyone is actively monitoring this interaction is beside the point. This distinction is crucial because it separates observation from perception. The boundary of the observable universe is not determined by human awareness, but by the possibility of physical interaction. Light arriving at our position in space can warm matter, initiate chemical reactions, or be registered by a detector, regardless of whether a person ever examines the resulting data. In this respect, the observable universe is a physical concept rather than a philosophical one, grounded in measurable processes, even as it evokes profound questions about the nature of knowledge and its limits. As we reflect on this idea, it can be useful to envision the observable universe less as a container and more as a growing archive. With each passing moment, new records are added as light from previously unseen regions finally completes its long journey to us. Some of these entries are ancient, chronicling events from the universe's earliest epochs, while others are more contemporary, capturing ongoing processes in galaxies that are relatively close. And just as any archive is inherently incomplete, defined by what was preserved versus what was lost, the observable universe is shaped by the light that has managed to survive its passage through expanding space. Certain signals diminish over their travels, others are absorbed, and some are stretched to the point of being nearly undetectable. Any observation is invariably filtered by the medium through which its information has traveled. This filtering effect does not render our observations unreliable. It simply underscores that interpretation requires meticulous care. Scientists dedicate immense effort to account for these phenomena, correcting for distortions and carefully distinguishing authentic signals from background noise. The outcome is not a flawless image, but it is a remarkably consistent one. Throughout the observable universe, the same laws of physics seem to operate universally. The same fundamental patterns recur, and the same kinds of particles, forces, and interactions appear time and again. This underlying uniformity gives scientists a certain confidence that the cosmos beyond our observational horizon is not fundamentally different, even though it remains beyond our reach. However, Confidence is not the same as certainty, and science maintains a clear distinction between what can be inferred and what can be directly observed. The word observable is what marks that very line. As we proceed, this definition becomes increasingly vital. When we discuss the size of the observable universe, we are not making a claim about the ultimate scale of all existence. Instead, we are describing the dimensions of the specific region that has revealed itself to us across light and time. That region alone is vast beyond any easy comprehension, containing hundreds of billions of galaxies, each with billions of stars, and each of those stars potentially orbited by planets. And yet, on a cosmic scale, it might represent only a small patch of a much larger whole. Grasping the meaning of observable allows us to hold both of these ideas simultaneously without contradiction. We can marvel at the immensity of what is visible, while also acknowledging the possibility that far more exists beyond the horizon we cannot yet traverse. There is a reason the universe feels so vast, even before we assign any numbers to its scale. That reason is tied less to the sheer volume of space and more to the speed at which information can travel through it. At the very core of the concept of an observable universe is a simple yet profoundly consequential rule. A maximum speed exists for everything. Nothing, regardless of its energy or exotic nature, can travel faster than light. This concept has become so familiar that it can almost sound commonplace, yet it represents one of the most significant limits in all of science. It governs not only the behavior of the universe, but also determines which parts of it we are capable of ever knowing. In a universe without this speed limit, the idea of an observable region would be meaningless. With this limit in place, observation becomes a function of patience, distance, and the unfolding of cosmic history. By any terrestrial standard, light travels at an incredible velocity. In just 1 second, a beam of light can circumnavigate the Earth more than 7 times. In the time it takes to blink, it covers a distance that would require a commercial airliner years to cross. And yet, when measured against the vastness of the cosmos, even this astonishing speed is revealed to be finite, restrictive, and ultimately defining. To truly appreciate the implications, it is helpful to slow this concept down rather than moving past it too quickly. Picture the universe in its first moments. Space and energy exist, and light starts to radiate outward in all directions from every point of activity. It does not, however, populate the entirety of space in an instant. Information spreads outward, much like ripples moving across a pond, but there is a profound distinction. The pond itself is stretching as the ripples travel. The unyielding speed of light introduces a lag between any event and our awareness of it. When something happens in the universe, that knowledge is not instantly available everywhere. A wait is always part of the process. This waiting period grows longer with increasing distance from the event's origin. This delay is not merely a technical limitation, it is a core characteristic of reality itself. There is no clever solution to bypass it, no feat of engineering, and no hidden shortcut through the cosmos. Even gravity, long suspected of acting instantaneously, has been shown to propagate at the speed of light as well. Therefore, when we gaze into deep space, we are not observing the universe as it is right now. We are, in fact, viewing a mosaic of different moments from its history. These moments are layered according to their distance. Nearby cosmic objects appear as they were in the relatively recent past. More distant objects are revealed as they existed in an increasingly ancient time. At the absolute limit of our vision, we witness the universe as it was shortly after its very beginning. This is why the speed of light functions as a sort of cosmic shutter. It restricts how much of the universe's story has had enough time to reach us. The observable universe is not defined by how far light could theoretically travel in a static, eternal cosmos. Its boundary is determined by the actual distance light has journeyed in a universe with a finite age, one that is in constant motion. If the universe had existed for an infinite time, our observable realm might also be infinite. Light from even the most remote regions would have had an eternity to arrive, but the universe has not been here forever. According to our best understanding, it had a beginning. From that initial moment, light has been traveling outward for a finite period. This fact alone imposes a fundamental boundary on what we can see. No matter how powerful our instruments become, we can never look beyond the distance light has managed to cover since the universe began. That boundary is not one we can push back by simply waiting longer or building better telescopes. It expands only as time itself moves forward. Here, the idea of a universal speed limit reveals its true significance. The speed of light is not just a measure of velocity, it is the rate at which causality itself spreads through space. It dictates which events are able to influence other events. It defines the boundary between what can be connected and what must remain separate. If an event is occurring right now in a galaxy beyond our observational horizon, it is causally detached from us. There is no possibility for that event to have an effect on us, and there is no way for us to know it is happening. The universe is simply not old enough for any signal, including light, to have crossed that immense divide. This also implies that the observable universe is not symmetrical through time. We see a great deal more of the past than we do of the present. In fact, we never see the present anywhere except for our own immediate location. Everything else is delayed by the time required for light to travel. That delay can be brief, or it can be immense. Light from the moon takes just over a second to arrive at Earth. Light from the sun needs about 8 minutes for its journey. Light from the nearest star beyond our sun requires more than 4 years. And light from distant galaxies travels for billions of years. At a certain point, this delay becomes so vast that we are no longer seeing mature stars or galaxies. We are instead seeing the primordial materials of the early cosmos, before stars even began to form. Beyond that point, we perceive a glowing fog of radiation. This is a remnant from when the universe was still intensely hot and dense. And beyond that, our observation comes to a complete halt. This is not because the universe ends there. It is because we have reached an epoch before light could travel freely. This cosmic speed limit also means that size in the universe is not purely a question of distance. It is also a question of time. When we state that an object is a certain number of light years away, we are describing both its distance and the duration of its light's journey. A light year is not a unit of time. It is a unit of distance that is defined by time. It is precisely the distance light covers in 1 year. That very definition incorporates the speed limit directly into the language we use. When cosmologists discuss the size of the observable universe, they are not measuring a fixed sphere. They are describing the current radius of a region. Its boundary is established by how far light has traveled since the beginning, while also accounting for the expansion of space. This is often where our intuition begins to struggle. If the universe is 8 billion years old, it seems logical to conclude that the observable universe has a radius of 13.8 billion light years. Light traveling for 13.8 billion years ought to cover 13.8 billion light years. The logic seems simple, but the universe has not been motionless during that time. Space itself has been expanding. While light was making its way toward us, the distance between us and the light source was also increasing. This means the light had to traverse what was effectively a moving target. As a result, the present-day distance to the most remote regions we can see is significantly greater than the distance light would travel in a non-expanding universe. The observable universe has a radius far larger than 13.8 billion light years. We will explore that concept more deeply later. The essential point for now is that the speed of light interacts with cosmic expansion in a way that stretches distances beyond what we might naively expect. Nevertheless, no matter how much expansion complicates the picture, the speed limit holds true. Light always travels at the same speed in its local frame of reference. Space can stretch and distances can grow, but no signal can ever overtake light. This leads to another consequence that is often overlooked. There are regions of the universe that we can see now, but which will not be visible forever. This is because the expansion of the universe is accelerating, driven by a mysterious influence known as dark energy. Some distant galaxies are receding from us so rapidly that light they emit today will never be able to reach us. We are only able to see them at this moment because their light started its journey long ago, when they were much closer. Future light from those very same galaxies will be carried away by the expanding fabric of space faster than it can travel toward us. Over immense stretches of time, they will gradually disappear from our view, slipping beyond our cosmic horizon. So, the observable universe is not only defined by a boundary in the past, it is also defined by a boundary in the future. The speed of light, combined with the expansion of the cosmos, creates a dynamic window of visibility. This window opens and closes across the eons. From a human standpoint, this is a strange concept. We are accustomed to thinking of sight as something that can always be enhanced. We imagine better lenses, larger mirrors, and higher resolutions. But no amount of technological advancement can overcome the finite speed of light or the finite age of our universe. Our view of the cosmos is not limited by human effort, but is instead governed by the fundamental nature of geometry and history. There is a deep humility in this realization. It suggests that the universe is under no obligation to grant us complete access to its workings. We perceive what we can from our unique vantage point in space and time, and nothing more. All knowledge is fundamentally local, even when it spans billions of light years. At the same time, the universe's ultimate speed limit provides the very structure for what we are able to comprehend. Because light travels at a constant velocity, it can be used as a cosmic standard of measure. By analyzing how light is altered on its journey, how it stretches, dims, or shifts in color, scientists can determine vast distances, cosmic motions, and the ages of celestial objects. None of these methods would be possible without that fixed speed. If light moved with infinite swiftness, there would be no travel time to measure, and no record of the past would be preserved in its transit. The universe would appear as a flat, two-dimensional image, entirely stripped of its temporal depth. What is so paradoxical is that the very limitation that confines our view is also what enables us to reconstruct the history of the cosmos. The finite speed of light, when considered across cosmic distances, effectively transforms the universe into a vast historical archive. Every photon that arrives at our instruments is a messenger, carrying a timestamp from the past. This timestamp reveals how long the light has been traveling and, by extension, the distance it has covered. By collecting a sufficient number of these messages from various distances, scientists can assemble a coherent timeline of the universe's long evolution. This is why the observable universe is not merely expansive but is also layered with time. The space nearest to us displays recent cosmic history, while the most distant reaches of space reveal ancient history. The speed of light imposes a natural, chronological order on everything we see. As this idea settles, it becomes easier to grasp why the observable universe is more than just everything we can see in this moment. It represents everything that has had enough time to make its presence known to us. That cosmic announcement is a continuous process. Even now, light is reaching us from regions that were once beyond our observational horizon. The observable universe is therefore growing, slowly but inexorably, as time moves forward. This growth, however, does not imply unlimited access. There will always be parts of the cosmos that remain beyond our reach, separated from us not by empty space, but by the unbridgeable gulf of time and cosmic expansion. There is a quietly counterintuitive quality to the way the universe presents itself. In our daily experience, we perceive distance and time as distinct concepts. An object can be far away without being ancient, and an artifact can be old without being physically distant. In the cosmos, these two ideas are inextricably woven together. The farther out into space we peer, the deeper into the past we are looking. Distance, in an astronomical sense, is not just a measure of space, it is a measure of history. This profound connection is a direct consequence of the cosmic speed limit. Because light propagates at a finite velocity, every observation we make includes a time delay. For nearby objects, this delay is minuscule, but for distant ones, it is immense, yet it is always present. No matter where a telescope is pointed, we are never seeing the universe as it is right now, with the exception of our immediate surroundings. We are always seeing it as it was at the moment the light began its long journey in our direction. This reality effectively turns astronomy into a form of archaeology. Instead of digging down through layers of soil to uncover the past, astronomers look outward through layers of time. Each increment of distance corresponds to an earlier chapter in the story of the universe. The stars nearby show us relatively recent happenings. Faraway galaxies reveal the conditions that prevailed billions of years ago. At the absolute edge of our observational capacity, we can witness the universe when it was still in its infancy, hot, dense, and unrecognizable compared to its current state. It is a concept worth pausing on, for it fundamentally reshapes our understanding of observation itself. When you look at something across a room, the time delay is so infinitesimal that it seems non-existent. Light traverses that short distance in a few billionths of a second, and your brain processes the image as happening in real time. Even looking at the moon, with its delay of about 1 second, does not meaningfully disrupt our sense of its presence. But as the distances become astronomical, these delays accumulate into staggering figures. The light from the sun takes 8 minutes to reach us. It takes hours to arrive from the outer planets, years from the nearest stars, and thousands of years from remote regions of our own galaxy. That journey extends to millions of years for light from nearby galaxies, and to billions of years for the most distant galaxies we can detect. On these scales, the notion of now loses its conventional meaning. The universe reveals itself as a mosaic of different epochs, all visible at once, layered one upon the other by distance. When astronomers mention that they are studying the early universe, they are not simply describing a process of reconstructing it from theory. They are directly observing it as it actually appeared in the distant past. The light arriving today from the most remote objects began its journey when the universe was just a fraction of its present age. This is the principle that leads to telescopes being described as time machines, though not in the way depicted in science fiction. They do not enable travel into the past. Rather, they permit observation of the past, and that is a critical distinction. This phenomenon violates no laws of physics or causality. It is merely a natural outcome of light's finite speed. A more powerful telescope does not allow you to see things more quickly. It allows you to see things that are farther away and therefore further back in time. When scientists construct larger mirrors or position observatories in space, they are not only seeking greater clarity, they are extending humanity's observational reach into earlier eras of cosmic history. This also explains why the most distant galaxies look so different from the ones in our cosmic neighborhood. They are not simply more remote versions of the same kinds of objects. They belong to a much younger universe. Many of these early galaxies are smaller, less organized, and more chaotic in their structure. They frequently lack the familiar, elegant spiral shapes seen in mature galaxies, because those complex structures had not yet had sufficient time to form. Stars, too, tell a story based in time. The very first stars were composed almost entirely of hydrogen and helium, the simplest elements forged in the aftermath of the universe's birth. Heavier elements like carbon, oxygen, and iron were created much later, deep inside the cores of stars, and were then distributed throughout space by powerful stellar explosions. When astronomers observe extremely distant stars or galaxies, they are often witnessing a universe that had not yet been enriched by multiple generations of stellar life and death. This layering of time across space provides a unique laboratory for scientists to test their theories of cosmic evolution. Instead of merely guessing how galaxies might have formed, they can look across vast distances and watch the process of formation unfolding at different stages. Nearby regions show us mature, fully developed structures. Distant regions reveal the earlier, formative steps. In this sense, the universe itself becomes the experiment. One of the most striking consequences of this is that there is no single, uniform age of the universe visible to us at any one time. The night sky is not a snapshot taken at a single moment. It is a profound collage, pieced together from images of countless different eras. Every point of light we see carries its own distinct timestamp. Even within our own Milky Way, which feels so much like home, the light from its different parts contains time delays that speak to its immense scale and history. The light that reaches us from stars near the heart of our galaxy has spent tens of thousands of years on its journey. When we gaze at that dense stellar region, we are witnessing it as it was when human beings were only beginning to populate the planet. Looking beyond the Milky Way, this effect becomes dramatically more apparent. Our view of the Andromeda Galaxy is a picture from approximately 2.5 million years ago. At that distant epoch, the earliest humans were just starting to fashion simple tools. The photons arriving on Earth now started their voyage long before any recorded history, and yet, by cosmic measures, Andromeda is a close neighbor, a member of our local galactic cluster. As astronomers peer even deeper into space, they find galaxies whose light embarked on its travel before the Earth even existed, preceding the formation of the Sun and before our own galaxy had settled into its familiar spiral form. At these immense distances, galaxies often appear as nothing more than faint, reddish smudges. The reason for this color is not that the galaxies are inherently red, but rather that the expansion of the universe has stretched their light waves over billions of years of travel. This stretching phenomenon, known as redshift, serves as a direct record of time. The more the light has been stretched, the longer its journey has been, and thus the earlier the cosmic era it reveals. In this way, redshift functions as a kind of cosmic clock. By carefully measuring the degree to which a galaxy's light has been elongated, scientists can calculate how long ago that light was first emitted. Distance, time, and the universe's expansion become deeply interconnected ways of measuring the same fundamental process. If we look far enough, eventually, the galaxies vanish from sight altogether. We reach a point in time when the cosmos was so young that the first stars had not yet ignited. Before stars existed, there were no galaxies to emit light. The universe was instead a uniform expanse of hot gas and intense radiation. The most distant light that we can possibly detect does not originate from stars or galaxies at all. It comes from a specific moment about 380,000 years after the universe began, a time when the cosmos had cooled sufficiently for light to travel without obstruction. Prior to this event, the universe was entirely opaque, more like a luminous fog than the transparent vacuum of space we know today. The light that was released at that moment has been traveling across the cosmos ever since. Over the vast expanse of billions of years, this primordial glow has cooled and stretched, now arriving at our instruments as a faint whisper of microwave radiation. This ancient light represents the absolute limit of how far back in time we are able to see. Beyond this boundary, the universe is invisible to any form of electromagnetic observation, not because nothing was there, but because light itself was trapped. The observable universe, therefore, possesses a boundary in time as well as in space. It reaches back to the instant that photons were first set free to travel unimpeded. Any event that occurred earlier than this remains concealed from our direct view. This makes the observable universe a chronicle not merely of space, but of cosmic evolution. It captures the universe at countless different ages, showing how complexity gradually arose from simpler beginnings. An early, uniform state gives way to the formation of structure. That structure then diversifies, eventually leading to the rich and varied cosmic environment we observe in our own galactic neighborhood. There is also a quiet sense of reassurance to be found in this perspective. It suggests that the universe holds its own memory. Events do not simply disappear once they have occurred. The evidence of their existence travels outward, preserved within light, crossing unimaginable distances. The universe, in a sense, remembers its own past, and we gain knowledge by interpreting these memories as they finally reach us. At the same time, this cosmic memory is inherently incomplete. Not every photon of light completes its journey. Some light is absorbed by intervening matter, some is scattered in different directions, and some is stretched to wavelengths that are beyond our ability to detect. The past that we receive is therefore a filtered one. It is a partial account, shaped by the very medium through which it has traveled. This is why the field of cosmology depends on identifying broad patterns rather than focusing on isolated events. No single observation can provide the complete narrative. But when taken together, observations from many different distances and eras combine to form a coherent picture of cosmic history. The same fundamental laws of physics appear to be consistent everywhere we look. The same basic relationships between cosmic properties repeat across space and time. This consistency is what enables scientists to weave disparate observations into a single, unified timeline. It also helps to explain why unexpected discoveries are so immensely valuable. When distant objects behave in ways that defy our expectations, it often indicates that we are observing physics operating under conditions that no longer exist anywhere nearby. The early universe was a place of far greater density, heat, and energy. Observing this ancient state allows us to test our scientific theories in extreme environments that are impossible to replicate on Earth. Looking far away, then, is more than an exercise in satisfying our curiosity. It is the primary method we have for learning about the origins of the cosmos and understanding the processes that led to its present state. Distance is transformed from an obstacle into a powerful scientific tool. As this concept settles, it becomes clear that the observable universe is not just vast in its spatial dimensions, it is profoundly deep in time. Every direction one looks is a voyage into the past, and every increase in distance represents a deeper step into cosmic history. From this realization, the story naturally progresses to the question of the universe's total age. If looking farther away reveals earlier periods, then how old is the entire cosmos? How do scientists determine a specific number for its age? And what does that number truly signify when time itself is so intricately woven into the act of observation? When the age of the universe is stated as 8 billion years, it can sound like a precise and final answer, as if a cosmic clock were consulted and a number simply recorded. The reality is that this figure is the culmination of decades of meticulous measurement, cross-verification, revision, and quiet scientific debate. It is neither a guess nor an arbitrary number. It is a value carefully pieced together from observations of light, motion, temperature, and the slow unfolding of cosmic history. To grasp what 8 billion years truly means, it is helpful to set aside our ordinary understanding of age. On Earth, determining age is often a straightforward matter. We celebrate birthdays. We count the years that have passed since a particular event. We rely on calendars that are anchored to familiar, repeating cycles. The universe, however, did not come with a birth certificate, and there was no one present at its inception to start a stopwatch. Everything we know about its age has been deduced indirectly, using the cosmos itself as the primary evidence. The fundamental starting point for this deduction is the expansion of the universe. The cosmos is not static. The fabric of space itself is stretching, carrying galaxies apart from one another. This critical fact, first recognized in the early 20th century, is the foundation of modern cosmology. When astronomers measure the light from distant galaxies, they discover that almost all of them are moving away from us. Moreover, there is a clear relationship. The farther away a galaxy is, the more rapidly it appears to be receding. This observed pattern is not about motion through space in the conventional sense. It is a consequence of the expansion of space between all objects. Once this expansion was firmly established, an unavoidable question arose. If the universe is expanding today, then it must have been smaller in the past. If one could rewind this process far enough, everything in the cosmos would have been much closer together. Following this line of reasoning to its ultimate conclusion, one arrives at an initial state where the entire universe was incredibly hot, dense, and compact. This insight formed the foundation of the modern Big Bang model. A crucial detail is that the Big Bang was not an explosion occurring within space, but was instead an expansion of space itself. There was no central point of origin and no outer boundary. Every region of the cosmos was simply much closer to every other region in the distant past. The age of the universe, therefore, is the measurement of time that has passed since that initial, intensely hot and dense state embarked on its expansion into the cosmos we inhabit today. But the question remains, how can we assign a specific number to that span of time? One technique involves determining the current speed of the universe's expansion. If you can ascertain the expansion rate today and understand how that rate has evolved through cosmic history, you can mathematically rewind the story of the cosmos. This is conceptually similar to reviewing footage of a balloon being inflated and calculating its starting point based on its rate of growth. The expansion rate in the present era is known as the Hubble constant. Despite its name, this value is not fixed across time. It simply describes how quickly galaxies are moving away from one another at this moment. Measuring it with high precision has proven to be a significant challenge. Different observational methods yield slightly different values, a discrepancy that continues to be an active field of scientific inquiry. Nevertheless, even with these uncertainties, the rate of expansion places a firm boundary on the universe's age. A more rapid expansion would suggest a younger cosmos, while a slower expansion points to an older one. When astronomers incorporate the most reliable measurements and factor in the changing speed of expansion over eons, they consistently calculate an age of approximately 13.8 billion years. Yet this measurement, as vital as it is, does not stand alone. Confidence comes from independent confirmation. One of the most powerful corroborating pieces of evidence is the oldest light we can detect, a faint microwave glow that permeates all of space. This radiation is a relic from the era when the universe, about 380,000 years after its beginning, first became transparent to light. The intricate pattern of minute temperature differences within this glow holds an immense amount of information, reflecting the density, composition, and geometry of the infant universe. When scientists apply well-established laws of physics to analyze these patterns, they can deduce how long the universe has been expanding since that primordial moment. The age calculated from this ancient light aligns with remarkable precision to the one derived from the expansion rate. A different line of inquiry looks at the most ancient objects known to exist. Certain stars are exceptionally old, having formed in the early chapters of cosmic history. By analyzing their chemical makeup and evolutionary stage, scientists can approximate how long they have been luminous. The age of these stars establishes a minimum age for the cosmos itself. Logically, the universe must be older than its oldest contents. When astronomers study the most ancient star clusters, they determine their ages to be in the range of 12 to 13 billion years. This finding leaves sufficient time for the universe to be slightly older, which is perfectly consistent with the 13.8 billion year figure. Had the universe been substantially younger, these stars would not have had enough time to form and evolve in the way we observe. What is perhaps most compelling is that these distinct methods are entirely independent of one another. They are built on different physical principles, different sets of observations, and different underlying assumptions, yet they all converge on the same approximate age. This powerful agreement gives scientists great confidence that the result is not an artifact of fitting data to a preferred outcome. It is also important, however, to clarify what this age signifies. When we speak of the universe being 13.8 billion years old, the reference is to time as measured along the grand arc of cosmic expansion. This does not imply that every location in the universe has experienced the passage of time identically. As we know, time itself can behave differently under varying physical conditions. In the very early cosmos, the conditions were extreme, with unimaginable temperatures and enormous densities. Physical laws operated in ways that have no direct parallel in our modern world. Our everyday experience of time is not a reliable guide for understanding those first moments. Still, the concept of an elapsed cosmic time remains a coherent and measurable quantity within our current scientific framework. It is also worth noting that the universe's age is not something we can see directly by looking to the farthest reaches of space. When we gaze at the most distant observable regions, we are not viewing a universe that is 13.8 billion years old. We are seeing it as it existed much, much earlier. The most ancient light we can capture comes from a universe that was less than 500,000 years old. The age of 13.8 billion years is a figure that is reconstructed, connecting those early observations with our present reality through a robust model of cosmic evolution. It is a synthesis of information, not a single snapshot in time. Another subtle but important point is that the cosmos did not begin in the state we see now. The very first fraction of a second after the beginning remains an area of deep mystery. While our current theories are incredibly effective at describing the universe from a tiny moment onward, they may not apply to the absolute earliest instant. When scientists state the age is 13.8 billion years, they are referring to the duration since the universe entered a phase that our physics can reliably describe, not necessarily from a philosophical absolute beginning. This distinction is critical because it frames the age as a physical claim, not a metaphysical one. It is a conclusion grounded in observable evidence. The universe today behaves as if it has been expanding for about 13.8 billion years, and that is what the age reflects. From a purely human standpoint, 13.8 billion years is a number so vast it is nearly without meaning. Our minds did not evolve to intuitively comprehend such immense timescales. We can articulate the words, but they lack a connection to our lived experience. To help make sense of this, people often use analogies, compressing cosmic history into a single calendar year or one day. While such comparisons can be useful, they might also foster a deceptive sense of understanding. The truth is, the age of the universe is not a concept meant to feel intuitive. It is a concept meant to be accurate. It is a number that arises from the consistent agreement across multiple, independent forms of evidence. For our journey of discovery, what matters is not the memorization of a number, but an appreciation for what that number makes possible. Knowing the universe's age enables scientists to set limits on the distance light could have traveled. This, in turn, establishes the scale of the observable universe and defines the maximum look-back time for our telescopes. Without a known age, the observable cosmos would be an undefined space. With it, our observations gain a coherent structure. This age also provides the essential timeline for all cosmic events. Galaxies did not materialize instantly. Stars required time to coalesce. Heavy elements needed even more time to be forged. The emergence of planetary systems, and eventually life, depended on billions of years of preceding cosmic evolution. The age of the cosmos provides the temporal backdrop against which all of existence has unfolded. As the universe matured, its fundamental conditions transformed. The initial expansion brought about a profound cooling. Matter began to coalesce under gravity. Structures started to form and grow. Over eons, the universe evolved toward greater complexity. The figure of 13. 8 billion years is more than a simple chronological marker. It serves as a measure of the immense transformation that has already taken place. There is also a certain quiet reassurance in understanding that the universe possesses a finite age. This knowledge implies there was a beginning, a time before the celestial objects we observe had come into being. It tells us that the night sky has not always appeared as it does now. It underscores that change is a fundamental aspect of reality, not merely an incidental one. At the same time, this age is not some kind of cosmic deadline. It offers no information about how much time is left. The universe is not aging toward a predetermined end in the way a biological organism does. Its ultimate fate is dictated by the dynamics of its expansion, its energy content, and other conditions that remain active areas of scientific inquiry. For the present, its age functions as a conceptual anchor. It weaves together the expansion of space, our astronomical observations, and the concept of distance into a single, cohesive narrative. Light has been journeying through space for 13.8 billion years. The cosmos has been stretching for that same duration. Our observable universe is ultimately defined by this shared history. As this concept takes hold, it becomes easier to grasp why cosmic size and age do not have a simple, direct relationship. If light has been traveling for 13.8 billion years, a natural question arises. Why is the observable universe so much larger than 13.8 billion light-years in diameter? At first, the numbers seem as if they should align perfectly, given a universe that is approximately 13.8 billion years old, and knowing that light covers 1 light-year annually by definition. It feels intuitive to assume that the most distant light we can detect must have traveled a corresponding distance of about 13.8 billion light-years. This intuition is perfectly understandable, but it is also incomplete. The observable universe is revealed to be vastly larger than such a straightforward calculation would suggest, and the explanation is rooted entirely in the behavior of space itself. To understand why, it is helpful to momentarily abandon the notion of space as a static, unmoving backdrop. In our daily lives, distances are constant. The space between two cities does not expand during a drive. The space separating two chairs in a room does not increase as you sit there. Because of this experience, we naturally tend to picture light traversing a fixed cosmic stage, steadily reducing the gap between its source and an observer. The universe, however, does not offer this kind of static framework. The very fabric of space is expanding. This expansion is not a phenomenon of objects flying apart from a central point through space. Instead, it is the space between objects that is increasing, everywhere at once. On a local level, galaxies are largely maintaining their positions, but the distances that separate large-scale cosmic structures are growing over time. The distinction is subtle, yet it is absolutely essential for understanding why the observable universe is larger than its age in light years. When a photon of light starts its long journey toward us from a remote galaxy, it is not crossing a fixed distance. The distance itself is actively changing while the light is in transit. As the universe expands, the space between the photon and its final destination stretches, which effectively lengthens the path the light must cover. What this means is that light emitted billions of years ago began its journey from a region that was significantly closer to our location than it is today. While that light was traveling, space continued to expand, carrying that distant region even farther away. By the time the light finally reaches our telescopes, its source is now immensely more distant than it was when the journey first began. So, When we observe light that has been in transit for 13.8 billion years, we are not stating that its source is currently 13.8 billion light years from us. We are saying that the light has been traveling for that duration through a cosmos that has been stretching continuously the entire time. This distinction is the very heart of the matter. To make this more tangible, imagine you are walking towards someone on a moving walkway, but the walkway itself is slowly stretching, pulling you and your destination apart. You maintain a steady walking pace, but the surface beneath your feet is moving backward. You are making forward progress, but not as rapidly as you would on solid ground. The longer the walkway operates, the greater the total distance you must cover. Light traveling through the expanding universe experiences a similar effect. It always moves at its constant local speed, but the space it is crossing is constantly changing over cosmic timescales. This effect becomes enormous. Consequently, the current distance to the most remote observable regions is not determined by a simple multiplication of light's travel time. It is determined by the complete expansion history of the universe. When cosmologists calculate the size of the observable universe, they incorporate this expansion. They create models showing how rapidly space has stretched at different epochs, how that expansion rate has changed as the universe evolved, and how light propagated through that evolving geometry. The result of these calculations is often surprising to those encountering it for the first time. The radius of the observable universe is not 13.8 billion light years. The actual radius measures approximately 46 billion light years. This means the full diameter of the observable universe is about 93 billion light years across. This finding does not imply that light traveled faster than its own speed limit, nor does it mean the universe violated its own physical laws. It simply means that while light was journeying toward us, the universe expanded in such a way that the distance between its starting point and its destination grew dramatically. The early universe plays a particularly significant role in this. Shortly after its beginning, the expansion was extraordinarily rapid. Space grew at a much faster rate in its initial stages than it does today. During that era, light was attempting to make progress through a cosmos that was expanding aggressively beneath it. As the universe cooled and evolved, the rate of expansion slowed for a very long time, only to begin accelerating again much later, driven by dark energy. Each of these distinct phases has influenced how far light could travel and how distances changed during its cosmic journey. Therefore, the size of the observable universe is not a simple product of speed and time. It is a cumulative result, an integral over all of cosmic history. It reflects how space expanded at every stage, while light was on the move. Another source of potential confusion arises from the very meaning of the word distance. Within cosmology, distance can be defined in several distinct ways, and the correct one depends entirely on what is being measured. One can speak of the total distance a photon of light has traveled. Alternatively, one might refer to the distance of an object at the precise moment its light was sent out. Then there is the distance to that same object as it exists today, after billions of years of cosmic expansion have carried it farther away. Each of these measurements is valid in its own context, but they describe different physical realities and cannot be used interchangeably. When the radius of the observable universe is stated as approximately 46 billion light years, this refers to a specific concept known as the current proper distance. It is a measurement of the space between us and the most remote regions whose light has successfully reached us. As that space exists today, not a measure of how far the light actually traveled. This distinction is important because it helps to correct a frequent misunderstanding. The observable universe is not some kind of bubble that is expanding into a surrounding void. Instead, it is a region of space-time defined by the parts of the cosmos that have had sufficient time to communicate with us. The vast distances involved are measured along the fabric of space as it is now. What this also means is that the observable universe can be significantly larger than the distance light has physically journeyed. These two quantities simply answer different questions. Light from the edge of our view has been traveling for 13.8 billion years. During that same period, space itself has been expanding. The combination of these two processes yields a present-day observable radius that is far greater than either number would suggest on its own. There is another subtle implication to consider. Certain regions of the universe are currently located more than 46 billion light years away from us, Assuming the cosmos extends beyond our horizon, these regions are real, but they remain unobservable. Their light has not yet arrived, and in some cases, it never will. The observable universe is therefore distinct from the universe as a whole. It is the result of an intersection between time, cosmic expansion, and causality. This clarification helps to show why asking about the edge of the universe can be misleading. The 4-6 billion light-year distance is not a physical wall. It is the present-day location of the most distant events whose light has had enough time to get here. As time moves forward, that boundary can shift, but its evolution is not a simple outward march. Because the expansion of the universe is accelerating, there are limits on how much larger our observable region can become. Some faraway areas are already receding so rapidly that any new light they emit will never be able to overcome the stretching of space and reach our world. The observable universe has a horizon, one that exists not only in our past but also defines our future. All of these ideas reinforce a central theme in cosmology. Size is a dynamic quality. It is dependent on when you take the measurement, how you define the distance, and how the universe has behaved throughout its history. The reason the observable universe is larger than 13.8 billion light-years is neither an exception nor a paradox. It is a natural outcome of existing within an expanding cosmos that has a finite age and a finite speed for information. As these concepts settle, the scale of the observable universe begins to feel less strange. The numbers cease to compete with one another and instead start to describe different facets of the same cosmic narrative. Time tells us the duration of light's journey. Expansion tells us how distances have changed over that journey. Observation tells us which regions are connected to us through that shared history. When people are first introduced to the idea of an expanding universe, the most common explanation they encounter involves a balloon. This analogy is simple, visual, and approachable, which is why it appears so often in classrooms, documentaries, and discussions among people trying to grasp an immense concept. But like all analogies, it is simultaneously helpful and deceptive. It illuminates certain features of cosmic expansion quite well while quietly distorting others. Understanding both sides is crucial if the size of the observable universe is to make intuitive sense rather than just sounding impressive. So let us take the balloon model seriously for a moment, not as a metaphor to be memorized, but as a tool for careful inspection. Imagine a simple balloon before it is inflated. You use a marker to draw small dots across its surface, where each dot represents a galaxy. At this point, the balloon is small, and all the dots are close to one another. Now, you begin to blow air into the balloon. As it grows, the surface stretches, and the dots move farther apart. No single dot is special. None of them is at the center of the surface. From the perspective of any one dot, all the other dots are receding. This captures something very significant about the actual universe. Galaxies are not flying away from a central point of explosion through empty space. On the contrary, space itself is expanding between them. From any given galaxy, the universe seems to be expanding uniformly. The farther away another galaxy is, the faster it appears to be moving away. This is not because it is traveling more quickly through space, but because there is more expanding space between the observer and that galaxy. In this regard, the balloon analogy functions very well. It demonstrates why there is no center of expansion within the universe. It shows why every observer sees themselves as the center of their own observable cosmos, and it illustrates how distances can increase everywhere at once without needing galaxies to travel through space like shrapnel from an explosion. It also helps explain why the universe looks the same in all directions on the largest scales. Just as the surface of the balloon stretches uniformly, the expansion of space preserves this large-scale consistency. Although smaller regions can be clumpy and structured, the moment we rely too heavily on the balloon, its flaws begin to show. The first limitation becomes obvious once you see it. The balloon's surface is two-dimensional, while the universe has three spatial dimensions. The analogy requires you to imagine living on the surface, not inside the balloon itself. That mental shift is manageable, but it already introduces an abstraction that can quietly distort our intuition. More importantly, the balloon expands into something. There is air outside of it and space surrounding it. In the real universe, There is no external space for the cosmos to expand into. Expansion is not a movement into an outside area. It is the stretching of space itself. This distinction is critical because the question, what is the universe expanding into, is a natural one, and the balloon analogy encourages it. The correct answer is that the universe is not expanding into anything. There is no external container. The expansion is an internal property of space. Another limitation becomes clear when we think about the speed of expansion. On the balloon, dots move apart faster as you inflate it more quickly, but the material of the balloon has its limits. If you stretch it too fast or too far, it will tear. Space does not behave like rubber. It possesses no material tension. It can expand without resistance, governed by the equations of general relativity rather than by physical elasticity. This difference is especially important when considering very large distances. On the balloon, no dot can move faster than the rubber allows. In the grand expanse of the cosmos, the fabric of space itself can stretch in such a way that very distant regions move away from each other faster than the speed of light, a fact that does not contradict any laws of physics. This phenomenon isn't about information or objects traveling through space at impossible speeds. Rather, it's about the amount of space between those regions increasing over time. This is one of the more counterintuitive ideas in cosmology, and the popular balloon analogy only partly captures its essence. If you were to imagine dots on a balloon's surface, you might think of their speed as they travel across the rubber. In the universe, however, this recession speed is not motion in the conventional sense. It represents the rate at which distance grows purely as a result of cosmic expansion. Another subtle point emerges when we consider the dimension of time. The balloon model often implies a single, smooth inflation from a small state to a larger one. The actual expansion history of our universe is considerably more complex. The rate of expansion has varied throughout cosmic history. In its earliest moments, the universe expanded with incredible rapidity. Following that, the expansion slowed down as gravity became the dominant force. More recently, a mysterious influence known as dark energy has caused the expansion to begin accelerating once more. The simple act of inflating a balloon doesn't naturally communicate these distinct phases unless one were to meticulously control the process. This analogy risks creating the impression of a constant rate of expansion, which is not what our universe has undergone. Without further clarification, the balloon can oversimplify the story of cosmic expansion, flattening its rich and dynamic history. There is also the matter of scale to consider. On a balloon, the dots are all more or less the same size in relation to the surface itself. In the cosmos, however, galaxies do not expand in unison with the space between them. The force of gravity is strong enough to hold galaxies, solar systems, and even atoms together. The expansion of space only becomes a noticeable effect over immense distances between great clusters of galaxies. If the balloon analogy is interpreted too literally, it can foster the idea that everything in the universe is stretching, including the objects within it. This leads to common misconceptions, such as the notion that people or the atoms they are made of are also expanding with the cosmos. They are not. On local levels, fundamental forces easily overpower the gentle pull of cosmic expansion. The balloon analogy also has difficulty illustrating the concept of cosmic horizons. On a balloon's surface, if you were to pick a starting point, you could imagine that with enough time and patience, you could eventually see or travel to any other point. This is not true for the real universe. Because the cosmic expansion is accelerating, there are now regions of space that are permanently beyond our observational or physical reach. Any light emitted from those distant regions today will never manage to cross the expanding gulf to arrive at our location. The balloon model does not have a natural way to represent this event horizon, a boundary beyond which events can no longer affect us, even with an infinite amount of time. This is where the analogy starts to break down in a more fundamental way. It can show expansion, but it fails to demonstrate the limits of causality. It depicts growing distances, but not the intricate relationship between the speed of expansion and the constant speed of light. Despite these limitations, the balloon analogy remains a valuable tool when used with care. It effectively grounds the idea that expansion is not an explosion moving outward from a central point into empty space. It helps to illustrate why the observable universe has no special center or preferred location. It also clarifies why the distances between galaxies grow, even though the galaxies themselves are not actively flying away from one another. The key is to see the analogy as a starting point for understanding, not as the final destination. One way to refine the model is to stop thinking of the balloon as a tangible object and instead focus on the rules that govern its two-dimensional surface. The important aspect is not the rubber or the air held within it. What truly matters is the mathematical relationship between points on that surface as it stretches. These relationships are a simplified mirror of the mathematical structure of expanding three-dimensional space. In this sense, the balloon is not a literal picture of the universe. It is a picture of the geometry of expansion. When scientists create mathematical models of the universe, they do not envision balloons. They work with equations that describe precisely how distances between points evolve over time, influenced by energy, matter, and the universe's overall geometry. The balloon analogy is simply a visual aid for one particular aspect of those complex equations. This distinction helps to prevent another common misunderstanding. The expansion of the universe does not imply that it began as a tiny point existing within some larger, ordinary space. The early universe was incredibly dense and hot at every location, not compressed into a single point surrounded by a void. The balloon analogy can inadvertently suggest a point-like origin if one pictures the balloon being completely deflated. In truth, the universe was never a point in space. Instead, space itself was different, smaller in scale, denser, and hotter. But it was still space. Understanding the limits of this analogy becomes particularly important when discussing the size of the observable universe. The balloon can demonstrate how distances increase, but it cannot tell you how far light has traveled on its journey to us, or how the expansion of space has affected that journey. It is unable to show why the observable universe is actually larger than its age in light years would suggest. It hints at the concept, but the details require moving beyond the metaphor. There is also a certain psychological comfort in the balloon analogy that can be misleading. Balloons are familiar objects. They can be held in our hands. They can pop. They have an end. The universe does not behave in this way. Its continued expansion does not suggest a fragility or an eventual tearing of space, at least not in any simple sense. The balloon analogy also tends to promote spatial thinking, where temporal thinking is what is truly required. Cosmic expansion is not just about where things are located in space. It is about how their relationships change through time. The observable universe is defined by that change, by the distance signals have been able to travel while space itself has evolved. When the analogy is employed carefully, with its limits clearly acknowledged, it becomes a helpful bridge rather than a conceptual trap. It starts the mind moving in the proper direction and then invites it to let go and instead follow the mathematics and the observational evidence. This is why cosmologists often return to the balloon metaphor while simultaneously issuing warnings against taking it too literally. It serves to open the door to a complex idea, but it does not furnish the entire room. There was a moment, very early in the universe's history, that quietly reshaped everything that was to come. It did not last long, and it left behind no direct photograph. Yet, without this event, the observable universe would be a radically different place from the one we now inhabit. This moment is known as cosmic inflation, and while the term itself might sound technical or abstract, the idea it represents is surprisingly tangible when approached with care. Cosmic inflation describes a very brief period when the universe expanded at an astonishing rate, far more rapidly than it does today. This was not the ordinary, gradual expansion that has unfolded over billions of years. Cosmic inflation refers to an extraordinary and sudden surge of growth that unfolded when the universe was unimaginably young. This event happened long before the first stars, galaxies, or even stable atoms came into being. To appreciate the significance of inflation, it is helpful to consider what the cosmos was like in its earliest moments, as far as our current evidence allows us to reconstruct. In its initial state, the universe was a place of extreme heat and density, where energy was the dominant force. The temperatures were so immense that particles were unable to coalesce into any lasting structures. Space itself was compressed into a state far smaller than anything we can observe today. The universe was already expanding at this point, but that expansion, on its own, fails to account for several remarkable features we now see. These characteristics presented a deep puzzle to scientists for many decades, and ultimately pointed toward the necessity of an idea like inflation. One of these puzzles centers on the universe's uniformity. When astronomers survey the cosmos on the largest possible scales, they discover that it appears remarkably consistent in every direction. The temperature of the early universe, which can be inferred from ancient radiation, is almost perfectly identical everywhere, showing only the most minuscule variations. This observation is quite surprising, because regions on opposite sides of the observable universe seem to have been too distant from each other to have ever exchanged energy or information through ordinary expansion. If light was unable to travel between these remote areas in the early times, it raises a profound question. How did they arrive at such similar conditions? This conundrum is known as the horizon problem. It implies that disconnected parts of the cosmos must have somehow coordinated their physical properties, even though standard expansion models suggest they were causally separated. Another puzzle is related to the geometry of space. Our observations strongly indicate that, on large scales, space is very nearly flat from a geometric perspective. This means that parallel lines behave as we would expect, and the angles within a vast triangle sum up in the familiar way. However, achieving this degree of flatness would have required exceptionally precise initial conditions if the universe had only ever evolved through ordinary expansion. Any slight deviation from perfect flatness at the beginning should have been amplified over cosmic time, resulting in a noticeably curved universe today. This extreme sensitivity to the initial state is called the flatness problem. It suggests that some process must have occurred early on to smooth out the geometry of space. A further issue involves the absence of certain unwanted relics. Many theoretical models predict that the very early universe should have produced a great abundance of exotic particles or structural defects, and yet, when we look out into the cosmos, we find no evidence of these relics. It appears that something must have acted to dilute them to the point of being undetectable. The theory of cosmic inflation offers a single, elegant solution to all of these puzzles. The core idea is that the universe experienced a phase of incredibly rapid expansion very early in its existence. During this fleeting interval, space expanded exponentially, increasing in size by a truly enormous factor in just a fraction of a second. As a result, regions that were once microscopic, uniform, and in close communication were stretched to astronomical scales. This stretching mechanism explains the observed uniformity. Before inflation began, the entire area that would eventually become our observable universe was small enough for all its parts to interact and settle into a state of equilibrium. Inflation then took this uniform patch and expanded it to cosmic dimensions, which is why it appears so smooth and consistent across vast distances now. The theory also accounts for the flatness of space. This rapid expansion flattens the cosmos in a way that is analogous to how inflating a balloon makes its surface appear flatter over any small area. Any curvature that might have existed initially becomes insignificant as space is stretched to such a tremendous size. Inflation naturally guides the universe toward a state of geometric flatness, regardless of its precise starting conditions. Regarding the unwanted relics, inflation effectively dilutes them. Any particles or structures that were present before this period of rapid growth would have been spread so thinly by the expansion that their density would drop to almost zero. This provides a compelling explanation for why we do not observe certain predicted phenomena today. What makes inflation particularly crucial to our understanding of cosmic scale is how profoundly it impacted the size of the observable universe. This was not merely a small addition to the ongoing expansion. It magnified distances on a scale that ordinary expansion could never match in such a short time. A region of space smaller than a proton could, through inflation, swell to a size larger than an entire galaxy. This all transpired at a very early moment, establishing the conditions for everything that came after. Because of inflation, the observable universe we see is vastly larger than it would have been if the cosmos had simply expanded at a steady rate from the beginning. The inflationary epoch stretched the fabric of space so completely that light emitted in the distant past had to journey across an already immense and still growing distance to reach us. This helps clarify why the observable universe has a radius of about 46 billion light-years, even though the universe itself is only 13. 8 billion years old inflation essentially gave space a significant head start. It created a cosmos that was already vast before ordinary expansion had much time to take effect. It is essential to stress that inflation does not contradict the universe's ultimate speed limit. During this period, nothing traveled through space faster than light in the conventional sense. Instead, it was space itself that was expanding. Distances grew because the metric of space was changing, not because objects were hurtling through it. This is a subtle but critical distinction. Inflation concerns the behavior of space-time, not the motion of objects within it. The cosmic speed limit applies to signals and particles moving locally through space. It does not place a constraint on how quickly space itself can expand. This is how inflation can separate regions faster than light could travel between them without violating any fundamental laws of physics. It alters the geometry of the universe, not the traffic within it. The evidence for inflation is indirect, yet it is quite compelling. The most powerful support comes from the specific pattern of tiny fluctuations observed in the ancient radiation that fills all of space. These fluctuations are a perfect match for the predictions made by inflationary models, which describe how quantum-scale variations would be stretched to cosmic proportions. Inflationary theory suggests that these small, quantum irregularities in the primordial universe were amplified, becoming the very seeds of all future structure. Over eons, gravity would act on these initial seeds, drawing matter together to form galaxies, clusters of galaxies, and the vast cosmic web. In this way, inflation provides a direct link between the smallest imaginable scales and the largest structures we observe in the universe today. It is a moment where quantum physics and cosmology converge, connecting the behavior of minuscule fluctuations to the grand distribution of galaxies across billions of light years. There are several different versions of inflationary theory, with each one proposing a slightly different mechanism or a different timeline for these events. Some models involve specific energy fields that drive the expansion, while others explore variations in how the inflationary period might have started or concluded. All these theories are united by a central concept, an incredibly swift expansion in the universe's earliest moments, which etched enduring signatures into the cosmos. We cannot see inflation directly, in the same manner that we observe stars or galaxies. Instead, its existence is deduced from the coherence it brings to our understanding. Cosmological models that incorporate inflation can account for many different cosmic characteristics simultaneously, all stemming from the same foundational principles. In its absence, explaining these same features would demand either highly improbable fine-tuning or a collection of disconnected theories. It's important to note that inflation is still a vibrant field of scientific inquiry. Researchers are constantly refining their models, hunting for more definitive evidence, and putting its predictions to the test. Observations in the future could validate particular inflationary scenarios, or perhaps uncover entirely new aspects of this process. For the discussion at hand, the most crucial consequence of inflation is its profound effect on cosmic scale. Had this event not occurred, the observable universe would almost certainly be dramatically smaller and significantly less homogeneous. The immense expanses we currently measure simply would not have come into being in their present form. Furthermore, inflation fundamentally alters our perspective on what might exist past the edge of our cosmic view. If space was stretched so radically in the beginning, it suggests that areas now far beyond our horizon were once our immediate neighbors. This implies the entire universe might be substantially larger than the portion we can perceive, potentially extending infinitely. Such a possibility is a natural outcome of inflationary theories. They frequently forecast a cosmos that continues well past our visible limits, positioning our observable sphere as just a single domain in a much grander reality. Yet, in a fascinating turn, inflation also underscores the inherent constraints on our ability to observe. Even if the cosmos is truly vast beyond what we can detect, inflation allows for those distant realms to be forever cut off from us. The expansion can create such a profound separation between regions that no light or information could ever traverse the void. In this way, inflation simultaneously expands the cosmos and draws its horizons closer. It is responsible for the immense size of the observable universe, while hinting that the total universe could be immeasurably larger still. There is a subtle elegance in this dual role. The very same mechanism that smoothed out the early cosmos and planted the seeds for all future structure also established clear boundaries on what any observer could ever hope to learn. Inflation did not render the universe completely transparent. Rather, it gave it a defined structure and an observational limit. Once this initial burst of growth subsides, a more conventional expansion begins to dominate. The universe continues to cool, allowing particles to coalesce, atoms to form, and light to finally separate from matter, starting its epic voyage through the cosmos. From that moment forward, the observable universe expands in a more predictable manner, dictated by the speed of light and the persistent stretching of space. The legacy of inflation, however, endures. Its signature is etched into the very scale of the cosmos we can see, into its remarkable uniformity, and into the cosmic web of structures that would eventually arise. Grasping the concept of inflation helps to reconcile the apparent paradox of an observable universe that seems too large for its age. It reveals that the universe's current size is not the outcome of simple, constant growth. Instead, it is the product of a rich and complex history, marked by moments of extreme change followed by vast epochs of slower, more gradual evolution. When we consider inflation, the sheer vastness of the observable universe begins to feel less like a mystery and more like a coherent story. The staggering numbers no longer seem so random. They start to represent a logical succession of physical events that played out one after another. When figures become astronomical, they have a tendency to elude our mental grasp. The scale of the observable universe is a prime example, a case where a number can be factually correct yet fail to make a meaningful impression. To state that the observable universe spans approximately 93 billion light-years across is a precise statement, but precision by itself does not confer comprehension. This figure requires context, careful explanation, and a degree of patience, as it describes a reality profoundly distant from our daily lives, yet one that is firmly rooted in meticulous observation. To start building an intuition for this scale, it is helpful to clarify exactly what the number signifies. When cosmologists refer to the observable universe being about 93 billion light-years across, they are describing its diameter, not its radius. From our vantage point on Earth, the farthest detectable areas are some 46 billion light-years away in all directions. If one were able to trace a line from one side of this observable sphere to the other, with our location at the center, that line would measure a total of 93 billion light-years. This simple fact immediately brings up a common point of confusion. How is it possible for anything to be 93 billion light-years in diameter when the universe itself is only 13? 8 billion years old? At this point, the groundwork for the solution may seem recognizable. While light from the farthest objects has been in transit for 13.8 billion years, the very fabric of space it was crossing has been stretching throughout its entire voyage. The separation between the light's origin point and our current position is now far greater than it was when the light first set out. This cosmic expansion has not proceeded at a constant rate. In the very early universe, particularly during the inflationary epoch, distances expanded with incredible speed. For a long time after, this expansion decelerated. In more recent cosmic history, it has started to speed up once more. The current dimensions of the observable universe are a reflection of the combined impact of all these different eras. Therefore, the 93 billion light-year measurement does not represent a distance that light has traveled. It is, instead, a measurement of the spatial separation as it exists in the present moment. The distinction is nuanced, yet absolutely critical. To hear the figure 93 billion light-years and envision light journeying from one edge to the other is to misunderstand the underlying physics. No photon has ever completed a journey from one side of the observable universe to the other. In reality, light from one edge has never had time to reach the opposite edge. These opposing regions remain causally isolated from one another. The diameter, then, is a statement about geometry, not a measure of potential connection. An alternative path to understanding this number involves looking at how it was determined. Researchers did not, of course, measure the observable universe with some kind of cosmic ruler. They deduced its size by synthesizing several key pieces of data: the age of the cosmos, its history of expansion, and the physical laws that describe how light propagates through a stretching spacetime. Employing models founded on general relativity, cosmologists are able to compute the current distance to a photon that was emitted long ago, factoring in the expansion of space over the course of its travels. When this method is applied to the most ancient light we can detect, the result is a present-day distance of approximately 46 billion light-years. This calculation rests on thoroughly vetted physics and a host of observations that independently corroborate the necessary parameters. It is not a delicate, singular finding, but one that arises with consistency from many different avenues of evidence. And yet, even knowing the derivation does not make the number feel any more tangible. A distance of 93 billion light-years is simply far beyond any scale our minds were built to process. Even the effort to visualize a single light-year can push our intuition to its limits. A single light-year is a measure of distance, equivalent to approximately 9.5 trillion kilometers. If you were to take that immense distance and multiply it by 93 billion, you would arrive at a figure of such magnitude that it ceases to function as a conventional number, shifting instead into the realm of pure concept. One way we attempt to manage this conceptual challenge is through the use of comparisons. For instance, if you could imagine the Earth scaled down to the size of a single grain of sand, the observable universe would still be larger than a major city. Another analogy suggests picturing the entire Milky Way galaxy as a dinner plate. In this scenario, the observable universe would extend far beyond any visible horizon. These thought experiments can provide a momentary sense of scale, but they tend to buckle under the sheer weight of the reality they try to represent. The difference in magnitude is simply too profound for such comparisons to hold. What becomes more important than visualizing the total expanse is appreciating what occupies it. Contained within that 93 billion light-year diameter are hundreds of billions of individual galaxies. Every one of those galaxies, in turn, holds anywhere from millions to trillions of stars. A great many of those stars are thought to host their own planetary systems. Many of these planets exist within environments that remain subjects of ongoing scientific study. Between the galaxies themselves are enormous regions of thinly dispersed matter. This matter is arranged into filaments and voids, which together constitute the largest known structures in the cosmos. And yet, for all that it contains, the observable universe is overwhelmingly empty. The average density of all its matter is astonishingly low. Galaxies are kept apart by truly enormous distances. The stars inside those galaxies are separated by expanses that dwarf the physical size of the stars themselves. Even the atoms that make up matter are composed mostly of empty space. The size of the observable universe, therefore, does not describe a densely packed volume. It describes an immense realm where structure exists as isolated islands adrift in vast oceans of near-perfect vacuum. Another fascinating aspect of this 93 billion light-year measurement is its symmetry. The observable universe appears to be roughly the same size no matter which direction we look. This uniformity is not because our location is special in any way. Instead, it is because on the largest scales, the universe looks statistically the same everywhere. From our vantage point, we reside at the center of a sphere with a radius of 46 billion light-years. From the perspective of another galaxy, that galaxy would find itself at the center of its own observable sphere. These spheres of perception overlap with one another, but they are not identical. Each observer in the cosmos has access to a slightly different portion of the total universe. This detail reinforces a critical idea. The observable universe is not some physical object floating in a void. It is better understood as a relationship, one that connects an observer to the rest of the cosmos, defined by the passage of time and the laws of causality. Its perceived size is entirely dependent on when and where the question is posed. As more time passes, the observable universe can indeed change, though not in a straightforward manner. Light from some regions we can currently see will continue its journey toward us. However, light from other, more distant regions will never reach us, no matter how long we might wait. This is because the expansion of the universe is accelerating. Consequently, the 93 billion light-year diameter is not a guarantee that our observations will one day encompass everything within that boundary and beyond. It is more like a snapshot, capturing what is visible to us now, based on the universe's current age and its specific history of expansion. There is also a common tendency to misinterpret the size of the observable universe. Many assume it represents a statement about the size of the entire universe, but this conclusion is not supported by evidence. The portion of the universe we can see could be just a small fraction of a much larger cosmic structure. It is also possible that what we see is representative of the whole, if the universe is finite but simply larger than our observational horizon. A third possibility is that the universe is truly infinite in its extent. Current observations are unable to definitively distinguish between these different scenarios. What the data does tell us is that, on very large scales, the universe appears to be geometrically flat. This observed flatness is consistent with both a very large, finite universe and one that is infinite. So, when we state that the observable universe is 93 billion light-years across, we are not making a claim that the universe ends at that boundary. We are simply stating the size of the cosmic region that has had enough time to reveal itself to us. An alternative way to consider this scale is by thinking in terms of time slices. The observable universe contains regions that exist at many different cosmic epochs. The regions closest to us are seen in a state that is close to their present condition. More distant regions are viewed as they were billions of years in the past. The farthest regions of all are seen as they existed when the universe was in its extreme youth. All of these different eras coexist within our single view of the observable universe. This is because the act of observation collapses both space and time into one composite image. The 93 billion light-year diameter does not represent a simultaneous picture of the cosmos at a single moment. It is, instead, an assembly of images gathered from countless different times. This perspective helps to explain why the observable universe can contain structures that formed at very different stages of cosmic evolution. Some of the galaxies we see appear fully mature. Others look primitive and are still in the process of forming. Some regions show vibrant and active star formation, while others are quiet and have long since evolved. All of these are visible to us simply because their light has finally reached our telescopes, not because they currently exist in the same state. This scale also serves to highlight how profoundly limited our own perspective truly is. Even within this 93 billion light-year expanse, there are regions with which we can never possibly interact. Light from one side of the observable universe will never have time to cross to the opposite side. No signal we could ever send out would be able to reach those distant edges. The principle of causality does not span the full diameter. This quality makes the observable universe less like a single connected territory and more like a personal archive of information that is accessible to us. Despite these limitations, the fact that the observable universe has a finite and measurable size is itself a remarkable achievement. It signifies that the universe possesses a structure that can be described in quantitative terms. It means that the field of cosmology is not merely a form of storytelling, but a science of precise measurement. The 93 billion light-year figure has been carefully refined over many years as our measurements have improved. Early estimates were far less precise. As observations of cosmic expansion, the cosmic microwave background radiation, and large-scale structure became more detailed, the calculation grew sharper. Today's estimate still has uncertainties, but they are relatively small when compared to the sheer magnitude of the number itself. That growing precision does not make the universe feel any smaller. If anything, it makes its vastness feel more tangible and concrete. There is also an undeniable emotional component to confronting this kind of scale. Some people find the idea unsettling, while for others, it can be a grounding experience. Understanding that the observable universe is so enormous can make personal concerns seem insignificant. Alternatively, it can make the fact of our own existence feel all the more extraordinary. Neither of these responses is inherently right or wrong. Scale has powerful psychological effects, and those effects will naturally vary from person to person. What is most important for the story we are following is that the size of the observable universe is not an arbitrary value. It follows as a logical consequence of the universe's age, its rate of expansion, and its early history. The period of inflation stretched space to incredible proportions. Expansion continued from there. Light traveled across the growing distances. The number 93 billion light-years is simply the present-day outcome of that long chain of cosmic events. From this point, the natural question begins to shift once again. Given the vastness of the observable universe, defined as it is by the limits of our sight, a profound question naturally emerges about what might exist beyond it. Does more of the cosmos extend past this horizon? If it does, how much more is there? And what can be stated about that unseen realm without resorting to speculation that is disconnected from evidence? The universe does not simply end at the boundary of the most distant light we can perceive. Nothing in the available evidence suggests the presence of a wall, an edge, or a sudden cessation of reality waiting just past the observable limit. What concludes at that point is not existence itself, but our ability to access it. The observable horizon delineates the boundary of what has been able to reach us thus far, not the boundary of what is actually out there. This is a simple distinction to state, yet it can be surprisingly difficult for our minds to fully internalize, because human intuition is so closely linked to the idea of boundaries. When we arrive at the edge of a map, our expectation is to find either a border or a space designated as unknown. The observable universe, in a physical sense, provides neither of these things. Instead, it presents a horizon defined entirely by the expansion of time and the finite speed at which information can travel. To better comprehend what may lie beyond that horizon, it is useful to first revisit what the horizon truly is. The observable horizon is not a physical place you could journey to and stand upon. It is not a material shell that envelops us in space. It represents the current distance to the most remote events, whose light has had enough time to arrive at our location since the universe became transparent. In present-day terms, that distance is approximately 46 billion light-years in every direction. Beyond that specific distance, light has not yet reached us. In certain cases, it never will, because the expansion of the universe is accelerating. So, when we ask what is located beyond the observable horizon, we are in fact asking what exists outside the reach of any causal connection with us. The most straightforward answer, based on everything we currently know, is simply more universe. Observations have shown that the cosmos appears remarkably similar in all directions we are able to see. On the larger scales, it seems to be both homogeneous and isotropic, which means it possesses roughly the same properties everywhere and in every direction. There is no evidence pointing to a special region, no sign that we are situated near an edge, and no indication that cosmic conditions change abruptly as we approach the observable limit. This profound uniformity is one of the most powerful clues we possess regarding what lies beyond our view. If the universe appears the same everywhere we can observe it, then it is a reasonable, though not provable, expectation that it continues in much the same manner beyond our horizon. This expectation is given a formal structure in what cosmologists refer to as the cosmological principle. This principle states that, on large scales, the universe is statistically identical everywhere. It is a principle that is not embraced without careful consideration. It is substantiated by a wealth of observation. Each time scientists peer farther and with greater detail, they discover the same general patterns repeating themselves. Galaxies tend to cluster in similar fashions. Large-scale structures adhere to similar distributions. The very same physical laws seem to operate everywhere from which light has managed to reach us. Consequently, when scientists discuss what might exist beyond the observable universe, they are not imagining wildly different physics or unfamiliar forms of space. They are cautiously extrapolating from what has already been seen. According to this view, beyond our observable horizon, there are more galaxies, more clusters, and more voids, all arranged in patterns that resemble those within our reach. These distant regions are not intrinsically special. They are simply too far away for their light to have completed the journey here. If cosmic inflation did occur, as current evidence strongly indicates, then the universe beyond our horizon might be vastly larger than the observable part. Inflation has a tendency to produce universes that extend far beyond the horizon of any single observer, often by an enormous degree. In many models of inflation, the observable universe is merely one small patch inside a much larger expanse. That expanse could be finite but extremely large, or it could potentially be infinite in its extent. At this time, our observations cannot conclusively differentiate between a very large finite universe and an infinite one. What they do reveal is that within the observable region, space appears to be very close to geometrically flat. A flat geometry is a feature that is consistent with both possibilities. If the universe is finite but substantially larger than the portion we can observe, then our horizon simply marks the current limit of our view. If the universe is infinite, then there is no overarching edge at all, and in that case, the observable universe is an infinitesimally small sample of a boundless whole. Either way, the observable horizon does not represent a boundary of existence. There is an additional point that is subtle but important. Regions beyond the observable horizon are not merely unseen, they are also causally disconnected from us. This means that no signal from them has influenced our region, and no signal from us has influenced them, at least, not yet. This causal disconnection has very real consequences. Events that happen beyond the horizon cannot affect us now. They are unable to shape our local environment. From a physical standpoint, they are irrelevant to our immediate future, even if they do exist. This can make the question of what lies beyond feel more philosophical than scientific. If we can never observe or interact with those regions, does it matter what is there? From a strictly experimental perspective, science deals only with what can, in principle, be observed. But cosmology also endeavors to create coherent models that explain why the observable universe looks the way it does. Those models frequently make statements about regions beyond the horizon as a natural consequence of their internal consistency. So while we cannot directly observe what lies beyond, we can make reasoned inferences that are based on well-tested theories. Another concept that often comes into the discussion at this point is the idea of multiple horizons. The observable horizon is not the only limit in cosmology. There is also what is known as the particle horizon, which marks the maximum distance from which particles could have traveled to us since the very beginning. Closely related to this is the event horizon, which marks the boundary beyond which events will never be able to influence us, even in the infinite future. Because the expansion of the universe is accelerating, the event horizon is particularly important. It implies that there are regions that are observable now, whose light has already reached us, but whose future light will never arrive. Over time, those regions will fade away from our view. So the set of things we are able to see now is not the same as the set of things we will ever be able to see. This adds a strange temporal twist to the observable universe. Some parts of it are temporary visitors in our sky, others are permanent. The horizon is not static, it evolves. Beyond the event horizon are domains of the universe from which we are permanently cut off. No matter how long the cosmos endures, a signal sent from those distant regions will never complete its journey to us. The barrier that isolates us is not one of distance alone, but is instead a fundamental consequence of the dynamics of cosmic expansion. This implies that our understanding of what lies past the observable horizon is shaped by which horizon we are considering. Beyond the particle horizon, there are places whose light is still in transit, not having had enough time to arrive. Yet beyond the event horizon, there exist regions whose light will never reach us at all. In either scenario, the core expectation is the same. There is simply no evidence to suggest that those unseen realms are fundamentally different from our own. They are merely beyond our perception. It is also easy to fall into the temptation of picturing the observable horizon as a kind of shell, constantly moving outward and revealing more of the universe as time unfolds. While this image holds a degree of truth, it can also be misleading. Because the expansion of the universe is accelerating, our observable sphere will never grow to include everything that exists. Given enough time, the horizon will not simply sweep across all of reality. Certain areas of the cosmos will always remain inaccessible. The observable universe, therefore, is not a growing bubble that will one day contain the whole, but rather a finite window defined by the long arc of cosmic history. This is not a limitation born from a failure of our technology or our imagination. It is an inherent feature of the very structure of the universe. From a purely human standpoint, this can feel deeply unsatisfying, as there is a profound desire to know what exists beyond every conceivable boundary. The observable horizon stands firm against this impulse. It is a boundary enforced by the laws of physics, not by a lack of knowledge. At the same time, the remarkable truth is that the existence of this horizon is what gives the science of cosmology its meaningful structure. If everything in the universe were observable, the entire field would lose its foundational framework. The presence of these horizons allows for precise statements to be made about causality, cosmic evolution, and scale. Another idea that sometimes emerges in these discussions is the possibility of different physical conditions in the regions beyond our sight. Some wonder if these areas could have different physical constants, alternate laws of nature, or different outcomes from the processes of the early cosmos. Certain speculative theories do entertain this notion, especially within versions of inflationary cosmology that propose different domains could settle into unique physical states. In such scenarios, our observable universe would be just one pocket among a multitude of others, each with its own distinct properties. These concepts are often gathered under the general term multiverse, though it is a word that encompasses a wide spectrum of very different proposals. It is important to approach this topic with care. While these ideas arise as a natural extension of some theoretical frameworks, they remain entirely speculative. As of now, there is no direct observational evidence that regions beyond our horizon operate under different physical laws. What we can state with a high degree of confidence is that within the vast expanse of our observable universe, the laws of physics appear to be consistent everywhere we look. This consistency provides strong support for extrapolating similar behavior beyond the horizon, at least as a reliable working assumption. The observable horizon also has a psychological impact that is easy to overlook, as it places our own location in a much broader context. We are not at the center of the universe in any absolute or privileged sense. We are simply at the center of our own observable region, just as every other observer throughout the cosmos is at the center of theirs. An observer in a galaxy beyond our horizon would perceive their own observable universe centered on their location, which would overlap with ours in some areas, while extending far beyond it in others. The profound implication is that there is no special vantage point. This symmetry is one of the most fundamental features of modern cosmology, as it removes any need for special places or preferred directions. The universe does not arrange itself around us. Rather, observation organizes itself around the observer. So, what lies beyond the observable horizon is most likely not a cascade of deepening mysteries. The most probable answer is simply more of the same. More space, more matter, and more cosmic history unfolding forever beyond our grasp. This does not render the question meaningless. It simply clarifies its scope. Science is able to describe the observable universe in extraordinary detail. Beyond that boundary, it can make cautious inferences that are grounded in consistency and theory. What it cannot do is provide direct measurements or images of regions from which we are causally disconnected. This is not a failure of science, but a boundary condition of reality. How many galaxies reside within this immense region? How are they arranged across space? And what does their distribution reveal about the scale we are attempting to comprehend? It helps to begin not with numbers, but with organization. The observable universe is not a uniform fog of matter spread evenly in every direction. It possesses a definite structure, and this structure exists across a vast range of different scales. We see it in stars bound together into galaxies, in galaxies drawn together into clusters, and in clusters arranged along immense filaments that are separated by enormous, empty regions. Understanding how these intricate structures fit together is the key to grasping what the sheer size of the observable universe truly contains. At the smallest scale relevant to this cosmic tapestry are the stars. Stars are the fundamental luminous building blocks of the visible universe. They are born when great clouds of gas collapse under their own gravity, igniting nuclear fusion in their cores and shining for millions or billions of years. Our own sun is just one example among hundreds of billions in the Milky Way galaxy alone. But stars are rarely found in isolation. Gravity consistently draws them into immense families, and these families are the galaxies. Galaxies themselves appear in a wide variety of sizes and shapes. Some are quite small, containing just a few million stars, while others are truly enormous, holding trillions. Spiral galaxies, such as our own Milky Way, are characterized by rotating disks with arms, where new stars are actively being formed. Elliptical galaxies are generally more rounded and tend to be populated by older stars. Irregular galaxies lack any distinct shape, often as a result of gravitational interactions or mergers with other galaxies. Within the observable universe, current estimates suggest there are hundreds of billions of galaxies. The precise number is always subject to change, depending on how deep our observations can penetrate and how faint an object must be to be counted. As our telescopes improve, this count naturally tends to rise, because faint and distant galaxies that were once invisible are finally detected. What is more significant than the exact number, however, is their distribution. Galaxies are not scattered randomly through space like dust. They follow intricate patterns that were shaped by gravity and the initial conditions of the early universe. Galaxies have a strong tendency to cluster together, forming groups and massive clusters that are all bound by their mutual gravitational attraction. Our own Milky Way is a member of a small collection known as the Local Group, which is home to dozens of galaxies, the largest of which are the Milky Way and the Andromeda Galaxy. Our own collection of galaxies is just one component of a far grander assembly known as the Local Supercluster, a structure that spans hundreds of millions of light-years. On an even more expansive view, galaxies and clusters do not appear randomly scattered, but instead trace out tremendous filaments, weaving together what we call the cosmic web. These filaments can stretch for incredible distances, sometimes hundreds of millions or even billions of light-years long. In the spaces between these threads lie enormous voids, vast regions of the universe where matter is exceedingly sparse and few galaxies reside. The emergence of this web-like pattern was not a matter of chance. It grew from minuscule density variations that existed in the very early cosmos. The inflationary period stretched these tiny fluctuations to astronomical proportions. Over eons, gravity amplified these differences, drawing matter into the denser areas and leaving the less dense regions to become emptier. What is remarkable about this cosmic architecture is its repeating nature across different magnitudes. Small collections of stars assemble into galaxies. Galaxies gather into groups. These groups merge into clusters. The clusters themselves are linked together by the great filaments, and these filaments delineate the immense voids. Each tier in this hierarchy is governed by similar physical principles, yet the scale shifts dramatically at every level. To better understand how these structures relate to the full size of the observable universe, a comparison of their volumes is useful. The Milky Way galaxy measures roughly 100,000 light-years in diameter. While this is immense from a human standpoint, it is incredibly small when set against the observable universe, which is estimated to be 93 billion light-years across. You could arrange nearly 1 million galaxies the size of the Milky Way, end to end, to span that diameter. Even this comparison fails to capture the true scale, because galaxies are separated by vast expanses of space. The typical distance between large galaxies is measured in the millions of light-years. Between clusters of galaxies, these distances expand to tens or even hundreds of millions of light-years. And between the largest filaments, the voids can extend for hundreds of millions of light-years, containing relatively little matter. Despite all this emptiness, the total mass within the observable universe is staggering. The vast majority of this mass is not found in stars or galaxies, but is instead composed of dark matter and dark energy. The ordinary matter that constitutes stars, planets, and ourselves accounts for only a very small portion of the universe's total contents. The formation of cosmic structure is deeply influenced by dark matter. This substance does not emit any light, but it does exert a gravitational pull. In the primordial universe, dark matter began to clump together before ordinary matter was able to. These clumps created gravitational wells that then pulled in surrounding gas, providing the seeds for galaxies to form. Without the presence of dark matter, the structures we can see today would not have developed in the same way. Dark energy, by contrast, shapes structure on the largest scales by affecting the expansion of the universe. It does not clump into objects. Instead, it acts as a uniform force that accelerates the expansion of space, which in turn limits the ultimate size that cosmic structures can attain over time. These components work in concert to sculpt the grand architecture of the observable universe. One way to conceptualize this scale is to imagine a continuous journey outward. At first, you would perceive individual stars. As you zoom farther out, these stars would blur together into the light of galaxies. Zooming out again, entire galaxies would appear as mere points of light within clusters. Continuing this journey, you would see the clusters themselves arranging into filaments and vast walls. Eventually, even these colossal structures would blend into a statistical haze rather than appearing as distinct objects. At the very largest scales we can probe, the universe begins to look smooth. Individual structures fade into cosmic averages. This smoothness does not mean that structure ceases to exist, but rather that the scale has become so immense that local variations are insignificant compared to the whole. This transition from a clumpy texture to a smooth one is a crucial observation. It indicates to scientists that the observable universe possesses a characteristic scale beyond which new, larger types of structure do not seem to appear. Above a certain size, approximately a few 100 million light-years, the cosmos appears statistically uniform. This uniformity is what allows cosmologists to define universal properties, such as average density, the rate of expansion, and the overall geometry of space. Without it, the very idea of a well-defined observable universe would be far more difficult to formulate. Another key aspect of cosmic structure is its relationship with time. The distribution of galaxies we see in the present has not always existed in this configuration. In the universe's distant past, matter was distributed much more evenly. The structures we see grew gradually over the course of billions of years. When we gaze into the far reaches of space, we are in effect looking back in time and seeing earlier phases of this cosmic evolution. Distant galaxies tend to look smaller, more irregular, and are often forming stars at a much higher rate. Large clusters are less common in the distant universe because they simply had not had enough time to fully assemble. This means the observable universe presents us with structures at many different stages of their development, depending on their distance from us. The nearby cosmos shows us mature, fully formed structures, while distant regions reveal younger, developing ones. All of these stages coexist within our view because observing the universe inherently mixes space and time. The scale of this structure also underscores a fundamental limitation. While the observable universe contains an incredible amount of complexity, it does not represent all of existence. It is possible that structures larger or rarer than anything we can see exist beyond our cosmic horizon. We have no way of knowing this directly. Nevertheless, the structures that are within our view already challenge the imagination. Some cosmic filaments span distances that are a significant fraction of the radius of the entire observable universe. Some voids are so vast that it would take light hundreds of millions of years just to traverse them. And yet, even these gigantic formations are small when compared to the full scale of the observable universe. They are merely features within it, not the boundaries that define it. Understanding galaxies and their place in this large-scale structure helps to ground the abstract figure of 93 billion light-years in something more concrete. That immense diameter is not a void. It is populated, patterned, and has been shaped by the interplay of gravity and cosmic expansion over billions of years. At the same time, acknowledging how sparsely matter is distributed helps to avoid a common misinterpretation. The observable universe is not a crowded place. It is predominantly empty space, punctuated by islands of matter that are connected by the faintest of threads. This delicate balance between vast emptiness and intricate structure is one of the most defining characteristics of the cosmos on its grandest scale. It demonstrates that sheer size alone does not dictate complexity. The universe succeeds in being both immeasurably vast and exquisitely organized. Long before the concept of galaxies clustering along invisible filaments became part of our scientific understanding, the cosmos was often pictured as either uniformly filled with matter or as a random scattering of objects. Neither of these simple images could withstand careful observation. What was revealed instead was something far more elaborate. It is a pattern so large that no single object can define it, yet it is so consistent that it appears everywhere we look on the most massive scales. This pattern is the cosmic web, and it stands as the largest known organization of matter in the observable universe. To truly grasp the cosmic web, one must first adjust their perspective. It is not a tangible object that can be captured in a single photograph. No telescope can ever show it all at once. Its existence is revealed only through the patient accumulation of data from vast surveys that map the positions of millions of galaxies. These individual maps are then stitched together to form a larger picture. Only when the distances become immense and individual galaxies fade into mere statistical points does the web become visible. At its heart, the cosmic architecture consists of four main components: filaments, nodes, sheets, and voids. The distribution of galaxies throughout space is not uniform. Instead, they gather along immense, thread-like filaments composed of dark matter and gas. Where these cosmic threads intersect, dense knots known as nodes begin to form. These nodes often serve as hosts for massive clusters of galaxies. Stretching between the filaments are the vast voids. These are enormous regions of space with a striking scarcity of galaxies. Some of these voids can span hundreds of millions of light years. This intricate arrangement is not for decoration. It is the inevitable result of gravity working across cosmic time. The force acted upon the minuscule density fluctuations left over from the era of inflation. These subtle, initial imperfections were the seeds that determined where matter would eventually collect and where it would become sparse. The web was not born in its present state. In the universe's infancy, matter was distributed with near-perfect smoothness. Only very slight variations in density existed, but they were subtle. Over eons, gravity gently coaxed material toward the slightly denser areas. These regions, in turn, grew even more dense. Their gravitational pull strengthened, drawing in more and more substance. Meanwhile, the less dense areas were gradually depleted of matter, growing ever more empty. This formation process follows a distinct hierarchy. The smallest structures were the first to coalesce. Larger structures came into being much later. They were built from the merging and accretion of these smaller precursors. As time passed, the filaments grew thicker, the nodes gained mass, the voids expanded as the matter within them was drawn away. What makes the cosmic web so significant for our understanding of scale is its sheer pervasiveness. It stretches across the entirety of the observable universe. A single filament can extend for hundreds of millions of light years. Chains of interconnected filaments can cover distances that are a considerable fraction of the observable universe's own diameter. And yet, what stands out is that these colossal features are themselves just components of a far greater whole. The web's specific details vary from place to place, but its overall structure is statistically consistent. Regardless of the direction astronomers point their instruments, the same fundamental pattern reveals itself. This underlying uniformity lends weight to the concept that our observable universe is likely a typical sample of a much vaster, unseen cosmos. The role of dark matter in this story is central. The cosmic web is, in essence, a structure made predominantly of dark matter. All the ordinary matter, the substance that makes up stars and planets, simply follows the gravitational framework established by this invisible substance. Gas is pulled into the dark matter filaments. Galaxies are born within these concentrations of gas. The light we see from galaxies helps us trace the web's outline, but it does not define the web itself. An intriguing detail is how well our computer simulations can replicate this structure. When scientists model the universe, starting with the conditions inferred from its earliest moments, and apply the known laws of physics, they see the cosmic web emerge naturally. Its simulated filaments, clusters, and voids are strikingly similar to what astronomers observe. This correspondence is deeply significant. It implies that the same fundamental physical laws are at work across an astonishing range of scales. The grandest structures in the cosmos arise from the very same force of gravity that dictates the path of a falling apple. It simply operates patiently over immense spans of time and distance. Another key characteristic of the cosmic web is its dependence on scale. Viewed up close, the universe is lumpy. Stars gather into galaxies. Galaxies collect into groups. At intermediate distances, clusters and even larger superclusters appear. Then, as we zoom out to the very largest scales, all of these individual structures merge into the coherent pattern of the web. Beyond a certain vast distance, the universe begins to appear statistically smooth. This transition point is of great importance. It enables scientists to calculate average properties for the cosmos as a whole. They can do this without getting lost in the details of local variations. The cosmic web, in this sense, imparts a rich texture to the universe while preserving its large-scale homogeneity. Grasping this structure also helps explain the ordered appearance of the cosmos. If matter had been scattered randomly, our view of the universe would be chaotic. It would be a much more challenging puzzle to solve. The web imposes order. It establishes predictable relationships between where galaxies are found and how they move. Those movements also contain a wealth of information. Galaxies are not static points within this structure. They are in constant motion. They stream along the filaments, drawn by gravity toward the dense nodes. By carefully measuring the velocities of galaxies, astronomers can map the underlying distribution of mass, including the invisible dark matter. This dynamic quality adds yet another dimension to our understanding of cosmic scale. The structures are not fixed. They are continuously evolving. Filaments channel material into clusters. Clusters coalesce with one another. Voids grow larger. In this way, the cosmic web can be thought of as a living pattern, one that transforms slowly over billions of years. The element of time becomes especially apparent when we account for distance. When we look at filaments that are relatively close to us, we are seeing them in a more mature, well-developed form. When we observe filaments at great distances, we are seeing them as they existed in the distant past. They appear younger, less defined, and more tenuous. The web, therefore, has its own chronicle. In the early cosmos, its filaments were more slender and less distinct. With the passage of time, they sharpened as more matter flowed into them. Simultaneously, the voids became larger and more vacant, increasing the contrast between the dense and empty regions. This means that our observable universe presents us with a tapestry of the cosmic web at many different evolutionary stages. The stage we see depends on how far away we look. The web we perceive in our cosmic neighborhood is ancient, compared to the fledgling web visible at the edge of our sight. In our observations, both of these eras exist at once. The immense size of the web helps to ground the concept of the 93 billion light-year observable universe. An individual filament might span hundreds of millions of light-years, yet it remains a small feature when compared to the whole. One could theoretically place hundreds of the largest known filaments in a line across the observable universe's diameter and still have space left over. This sense of scale helps to correct a common misunderstanding. Seeing the largest known cosmic structures can sometimes lead to the false assumption that they represent the universe's boundaries. They do not. They are simply features contained within the cosmos, not its outer edges. Furthermore, the cosmic web helps us appreciate that cosmic emptiness is not the same as absolute nothingness. The great voids are not literal holes carved out of space. They are simply regions where the density of matter is exceptionally low, but never zero. Even in the most desolate voids, one can still find traces of dark matter, thin gas, radiation, and the fundamental expansion of space-time itself. Voids are consequential because they actively influence the flow of matter around them. As they expand, they effectively push material toward the surrounding filaments. Their existence shapes the web's geometry just as profoundly as the dense clusters do. It is easy to picture the cosmic web as a fixed, unchanging lattice. However, such a static image fails to capture the dynamic, ongoing process of cosmic evolution. The web is not a rigid framework. The cosmic web is the outcome of a delicate balance, a perpetual contest between competing influences. On one side is gravity, the relentless force pulling all matter inward. On the other is the expansion of space, constantly stretching the universe apart. Dark energy acts as an accelerant to this stretching across the largest cosmic distances. As the rate of expansion increases, the growth of cosmic structure gradually slows. The immense filaments of galaxies will not continue to thicken indefinitely. Galactic clusters will eventually cease merging as expansion begins to dominate gravity's pull over vast scales. Over extraordinarily long stretches of time, this process may cause the web to become more diffuse, its structures drifting apart faster than gravity can ever connect them. This future evolution of the cosmos adds another fascinating layer to our understanding of scale. The observable universe we perceive today is a snapshot from a specific cosmic era, a time when large-scale structure is not only prominent, but also actively evolving. In the distant past, the web was much fainter. In the far future, it may dissolve into isolated islands of matter, separated by an ever-widening expanse of empty space. Even in our present moment, the web is not uniformly accessible to us. Some filaments stretch far beyond our observational horizon. We can only perceive the portions whose ancient light has had sufficient time to reach our telescopes. The web presumably continues beyond that horizon, following similar universal patterns, yet it remains forever beyond our capacity for direct observation. This reality reinforces a recurring theme in cosmology. The observable universe reveals profound patterns, but it does not show us the complete picture. We can see enough to discern the underlying rules of the cosmos, but not enough to view the entire cosmic stage. The cosmic web also plays an interpretive role, helping to explain why the observable universe possesses a characteristic size. The web itself materializes within the causal boundary established by cosmic expansion and the finite speed of light. Structures exceeding a certain immense scale simply cannot form because information and gravitational influence are unable to travel quickly enough across those distances to coordinate their assembly. In this sense, the observable universe is not merely a passive vessel containing all of this structure. Its very size is an active participant, shaping the kinds of structures that can exist within its boundaries. As this comprehensive picture comes into focus, it becomes easier to appreciate how scale operates in distinct but interconnected layers. Stars are bound together into galaxies. Galaxies are gathered into clusters. Clusters are strung along colossal filaments. These filaments trace the grand design of the cosmic web. The web, in turn, fills the observable universe, and the observable universe itself might be just one small portion of a much larger, unseen reality. Each of these layers adheres to the same fundamental laws of physics, but those laws manifest in different ways depending on the scale. This layered organization is not immediately apparent when considering the raw numbers alone. It only emerges when one contemplates size, structure, and cosmic evolution as a unified whole. The cosmic web serves as the essential bridge, connecting abstract cosmological measurements to a tangible physical reality. With these largest of all patterns now in view, another question naturally arises. If the observable universe contains such immense structures, and if those structures appear to be arranged without any preferred direction or center, then where are we located within this magnificent tapestry? From our vantage point here on Earth, it is almost impossible not to feel as though we are at the very center of it all. In every direction we look, the observable universe extends outward for tens of billions of light years. We see distant galaxies receding away from us uniformly, no matter where we aim our instruments. The cosmic microwave background radiation appears nearly identical across the entire sky. From our perspective, it truly seems that we occupy the middle of everything that can possibly be seen. And yet, this powerful impression is an artifact of perspective, not a statement of privilege. The sensation of being at the center arises as a natural consequence of how observation functions within an expanding universe. For any observer, anywhere in the cosmos, light arrives from all directions at the same finite speed. This simple fact automatically places that observer at the center of a sphere, one defined by the maximum distance light has traveled since the universe first became transparent. This sphere is what we call the observable universe, and its fundamental geometry guarantees that every observer, regardless of their location, will perceive themselves to be at its center. This does not imply that we occupy a special place in the cosmos. It simply means that all observation is inherently local. To understand why this distinction is so crucial, it is helpful to imagine another observer on a distant planet, in a galaxy billions of light years away from our own. That observer would also see galaxies receding from them in all directions. They too would measure a nearly uniform cosmic background. They would also calculate the boundaries of an observable universe, with themselves situated precisely at its center. Their observable universe would overlap with ours in many regions, but it would also include vast areas that we cannot see, while excluding some regions that we can. Neither observer's perspective is incorrect. Both are perfectly valid within their own frames of reference. This symmetry is one of the most profound lessons of modern cosmology. There is no absolute, physical center of the universe. There is no preferred location from which the cosmos unfolds. The laws of physics appear to be the same everywhere we are able to look, and we have no evidence to suggest this changes beyond our cosmic horizon. The notion that Earth or humanity holds a central position in the universe has a long and storied history. For most of human existence, it was a perfectly natural assumption that we stood at the heart of creation. The sun appeared to circle the Earth, and the stars seemed to be fixed upon a celestial sphere that rotated around us. This worldview was not foolish. It was a logical conclusion based on everyday, unaided observation. As our measurements became more precise, however, those foundational assumptions were challenged and, eventually, overturned. We discovered that Earth orbits the Sunday. We learned the Sun is just one star among many in the Milky Way galaxy. And we found that the Milky Way is but one galaxy among countless others. Each of these scientific revolutions displaced us further from a perceived center. Modern cosmology completes this process. It reveals not only that we are not at the center of the galaxy or the universe, but that the very concept of a central location loses its meaning on cosmic scales. The expansion of the universe does not radiate outward from a single point in space. It happens everywhere at once. The fabric of space itself stretches between all distant regions simultaneously. From the perspective of any galaxy, all other distant galaxies appear to be receding. There is no unique origin point for this expansion within space itself. This idea is often difficult to reconcile with our intuition because the explosions we experience in daily life all have centers. Fireworks burst outward from a single point. Shock waves propagate from a source. The Big Bang is frequently misconstrued as this kind of event. In reality, it was not an explosion in space, but rather an expansion of space. Because of this, asking where the Big Bang happened is like asking for the center of the two-dimensional surface of a sphere while standing on the surface itself. The question assumes a frame of reference that simply does not apply. The reason it feels as though we are at the center of the observable universe is because the observable universe is, by definition, relative to us. It is not a static object with a fixed position. It is the complete set of all cosmic events whose light has had time to reach us. If you change the location of the observer, the observable universe changes as well. This perspective can feel unsettling at first, as it removes the comfort of a global, universal frame of reference. There is no cosmic coordinate system with a clearly marked origin. What exists is a collection of local observations, all connected by a set of shared physical laws. At the same time, this is a deeply unifying realization. It signifies that no single observer holds a special position. Every observer, located anywhere in the cosmos, has access to an observable region with a fundamentally similar structure. The universe does not single out any particular viewpoint. The uniformity of the cosmic background radiation powerfully reinforces this concept. When astronomers measure the faint, ancient light left over from the early universe, they discover that it is almost perfectly identical in every direction they look. There are minuscule variations present, but no large-scale gradient exists that might point toward a cosmic center or an edge. If we were situated near a special location, we would expect to observe distinct asymmetries. One direction in the sky might look fundamentally different from another. The expansion itself might appear to behave differently depending on where we aimed our instruments. None of this has ever been observed. Instead, the universe appears statistically the same everywhere, at least within the confines of our observable region. This quality, known as isotropy, supports the conclusion that our location is typical, not exceptional. There is also a critical distinction to be made between being at the center of observation and being at a center of mass or geometry. In a universe that is homogeneous on its larger scales, concepts like a center of mass lose their conventional meaning. There is no single point that everything revolves around. Mass is distributed with remarkable evenness when averaged over sufficiently vast volumes of space. The universe's geometry behaves in a similar fashion. Space can be flat, curved, or open without demanding a central point for its structure. In a flat or infinite universe, a center simply does not exist. In a universe that is finite yet unbounded, like the surface of a sphere extended into higher dimensions, a center exists only in a mathematical sense, outside the space itself, not within it. From any location inside such a space, no point is distinguished as being central. So, when we say it feels as though we are at the center, what we are truly describing is the way observation organizes itself symmetrically around the observer. This is not a statement about the structure of the universe. It is a statement about how information reaches our location. This distinction becomes even clearer when we consider the mechanism of redshift. Galaxies that are farther away appear to be receding from us faster in all directions. This can easily look like an expansion radiating outward from our specific point. In reality, it is a direct consequence of a uniform expansion happening everywhere. Any observer, anywhere, would measure the very same pattern. If we were able to instantly relocate to a distant galaxy, we would witness the same behavior, but it would be centered on our new location. The universe is indifferent to where you stand. Its expansion looks the same from everywhere. This idea also resolves a common source of confusion. People sometimes ask if we are moving through space, away from some central point of origin. On cosmic scales, we are largely at rest with respect to the expansion itself. We are being carried along with the stretching of space-time. Our local motions are quite small when compared to the vast scale of cosmic expansion. The feeling of centrality also interacts with the concept of the observable horizon. Because this horizon is centered on the observer by its very definition, it creates a natural visual boundary. Everything we are able to see lies within a perfect sphere centered directly on us. This can reinforce the illusion that we occupy a privileged position. But that boundary is not a fixed feature in space. It is a boundary defined by time. If another observer were to calculate their own horizon, it would be centered on them, not on us. This leads to a subtle but important realization. The observable universe is not a feature of the universe alone. It is a feature born from the combination of the universe plus an observer. A psychological component is at play here as well. Human perception is inherently egocentric. We experience the world from a single, personal point of view. Our brains are wired to treat our own location as the primary reference point. That instinct naturally carries over into our cosmic thinking, unless it is carefully and consciously examined. Cosmology challenges that instinct by demonstrating that the same view emerges from any location. What feels like our own centrality is actually a property of universality. Even the phrase, "our observable universe," can be misleading if taken too literally. It does not belong to us in some exclusive sense. It is simply the observable universe, as seen relative to our location and our moment in time. This realization has profound implications for how we interpret large-scale cosmological data. When scientists create models of the universe, they do not assume our position is special. They assume it is typical. This assumption is not a philosophical preference. It is a testable hypothesis. If our location were in fact unusual, our observations would reflect that. So far, they do not. This does not imply that the universe is boring or featureless. Local variations certainly exist. Great clusters of galaxies, immense voids, and cosmic filaments create a rich and complex tapestry. But on sufficiently large scales, those variations average out into a smooth, consistent whole. Being at no special location also means the laws of physics discovered here are very likely universal. The same processes that govern stars, galaxies, and the expansion locally should apply everywhere that light has had time to reach us from. This universality is one of the foundational reasons cosmology can make confident statements about regions that are incredibly far away. It relies on the assumption, which is strongly supported by observation, that physics does not change abruptly from one part of space to another. The sense of not being central can feel deflating, but it can also be grounding. It places us firmly within the universe rather than above it. We are participants in cosmic evolution, not spectators standing outside of it all. At the same time, the fact that the observable universe centers itself around each and every observer gives every location a kind of equal significance. No matter where you are, the universe unfolds around you in the same fundamental way. This balance between humility and inclusion is one of the quiet philosophical consequences of modern cosmology. We are not at the center of the universe, but the universe presents itself to each observer as though they were. As we continue, this perspective naturally raises another question. If there is no center and no edge in the usual sense, does the universe have a boundary at all? Is the observable horizon merely a limit of our vision? Or does it hint at something deeper about the universe's ultimate shape and extent? Edges are familiar to us. Rooms have walls, maps have borders. Even abstract systems often come with limits that can be pointed to and named. Because of that, it feels natural to ask whether the universe has an edge, a place where space simply stops. Once the observable universe has been described as being finite in size, the question almost asks itself, if there is a boundary to what we can see, is there also a boundary to what exists? To approach this carefully, it helps to separate two very different ideas that are often tangled together. One is the edge of observation, the other is an edge of space itself. It is essential to distinguish between the observable horizon and a cosmic edge, as these are not the same concept, and confusing them is the source of many common misconceptions about the universe's scale. The observable horizon, as we have explored, is fundamentally a limit defined by the age of the universe and the finite speed of light. It represents the maximum distance from which information has had time to reach us since the cosmos first became transparent. This horizon is not a physical barrier. It does not impede travel, nor does it reflect light back at us. It is, quite simply, the present boundary of our causal contact with the rest of the universe. An edge, by contrast, would be an entirely different phenomenon, representing a true physical or geometrical boundary. This would be a place where space itself comes to an end, where the concept of moving farther is meaningless, or where the fundamental rules of geometry undergo a sudden change. Crucially, nothing in our current observations requires that such an edge must exist. In fact, every piece of available evidence indicates the contrary. On the largest scales that we can survey, space appears remarkably smooth and consistent. The same types of large-scale structures repeat, and the same laws of physics seem to apply everywhere. There is no indication that we are nearing some great divide where conditions shift or physical behaviors are altered. What is remarkable is that the universe does not appear to be thinning out or curling in on itself near the limits of our vision. It simply seems to continue on, as far as the evidence allows us to perceive. This is one of the primary reasons why cosmologists are so careful when using the word edge, as it carries implications that are not supported by the physics of our cosmos. To grasp why an edge is not a necessary feature, it is helpful to think in terms of geometry instead of relying on everyday intuition. In our daily experience, space feels flat and boundless. One can, in principle, walk in a straight line forever without running into a boundary. However, other geometries are entirely possible. A classic illustration is the surface of a sphere. From the perspective of a creature living on that two-dimensional surface, there is no edge. It is possible to travel in any direction and never encounter a barrier. Despite this, the surface itself has a finite, measurable area. It is a world that is limited, yet unbounded. The universe could operate on a similar principle, just in higher dimensions. It is conceivable that space is finite in its total volume, but has no edges, wrapping back on itself in a way that eliminates the need for a boundary. In such a cosmos, traveling far enough in a single direction could theoretically bring you back to your point of origin. Although the distances involved would likely be far greater than the entire observable universe, this idea, while difficult to visualize, is mathematically sound and consistent with what we know about physics. Alternatively, space could be genuinely infinite. In this scenario, an edge is absent, simply because there is no end. Space would just extend without limit in all directions. The observable universe would then be just one finite patch within an endless expanse, its boundaries defined by what we are able to see rather than by what truly exists. At present, our observations cannot definitively distinguish between these possibilities. Measurements of cosmic geometry suggest that space is very, very close to being flat. A flat geometry is compatible with both an infinite universe and a finite one, so immense that its curvature is too subtle for us to detect from our vantage point. What is important here is that neither of these leading models requires an edge to exist. The absence of an edge is further supported by the mechanics of cosmic expansion. The universe is not expanding into something else. There is no surrounding void waiting to be occupied. Expansion is the stretching of space itself. To ask where the edge of this expanding space is located presumes the existence of an external frame of reference, which the universe does not provide. This is why questions such as, "What is the universe expanding into?" do not have meaningful answers within the framework of current physics. Expansion does not necessitate an external container. Space does not need a place to go. It simply changes its own internal geometry over time. An edge would imply an outside, and current models do not include one. There is another subtle point that is often overlooked. Even if the universe were finite and did possess some kind of global boundary, that boundary would not necessarily be observable or reachable. Depending on the specific geometry and the dynamics of expansion, it could be permanently hidden beyond our cosmic horizons. So, even in speculative scenarios where an edge does exist, it would not behave like a wall that one could approach or see. It would not be a part of the observable universe in any direct sense. This brings us back to the observable horizon, which can feel like an edge because it represents a limit on our access to information. But a limit on access is not a limit on existence. Such horizons tell us where our information stops. not where reality itself stops. To make this distinction clearer, one might consider the horizon here on Earth. When standing on a flat plane, the horizon delineates the limit of your vision. Beyond that line lies more land, more ocean, and more features that are simply hidden from view by curvature and perspective. The horizon feels like an edge, but it is not. The cosmic horizon functions in a similar way, though the mechanism is different. Instead of the curvature of the Earth blocking our sight, it is the combination of time and expansion that limits the information we can receive. The analogy is not perfect, but the core lesson is the same. A horizon does not imply an edge. The persistent idea of an edge also has historical roots. Some early cosmological models did, at times, depict the universe as a finite sphere expanding into an empty space. These have since been replaced by models that do not require an edge. Modern cosmology is comfortable with the notion that the universe may not have a boundary in the conventional sense. This comfort is born from consistency. The mathematics is sound, and the observations align. There is no need to introduce an edge to explain what we see. That being said, there are speculative ideas that do explore boundaries or transitions. Some theories propose that our universe could be embedded within a larger structure, or that space could have different phases beyond certain regions. These ideas remain highly theoretical and are without direct observational support. While they are interesting to contemplate, they do not arise from any scientific necessity. What science currently supports is a simpler picture. The universe, as far as we can observe, does not show any signs of an edge. It behaves as though it extends beyond our horizon in much the same way it exists within it. This does not make the universe boring or perfectly uniform in every detail. Local variations are abundant, complex structures form, and cosmic evolution continues. But on the specific question of edges, the evidence points toward continuity rather than termination. Another reason an edge feels so intuitive is because the size of what we can see has been quantified. Once we state that the observable universe is about 93 billion light-years across, it can sound like a container with defined dimensions. Containers typically have walls, but this number describes the extent of our reach, not the boundaries of an enclosure. The observable universe is not some kind of container. Rather, it is a sphere of perception centered on whoever is looking, its boundary defined by the history of cosmic expansion and the time it takes for light to travel. If you change the location of the observer, that sphere of perception also changes. The concept of an edge applies to an object, but the observable universe is not an object, it is fundamentally a relationship. This insight completely reframes the inquiry. Instead of asking where the cosmos has an end, a more precise question is how far our observations can reach, and how that reach evolves over time. As the universe ages, our observational horizon might expand in certain directions while simultaneously shrinking in others, a consequence of accelerating expansion. This means that some regions we can see today might become forever unseeable in the future. Conversely, areas that are currently beyond our view may never come into it. This dynamic quality is profoundly different from the behavior of a fixed edge. An edge is static, while a horizon is fluid. There is also a certain emotional pull to the notion of an edge, as edges seem to provide a sense of closure, making a system feel contained and complete. A universe that lacks a final border can seem unsettling because it defies this desire for completion, offering no ultimate boundary to orient against. Yet, cosmology is not in the business of offering comfort. Its purpose is to describe what is consistent with the available evidence. From this perspective, the absence of an edge is not a philosophical declaration, but a practical conclusion. To introduce a boundary where one is not needed would only complicate our models without adding any explanatory power. Should future observations ever uncover evidence of some kind of boundary, the field of cosmology would certainly adapt. Science does not hold to the idea of an edgeless universe as an article of faith. Its commitment is to following the evidence, and so far, that evidence consistently points away from any sort of edge. The question of whether the total universe is finite or infinite, however, remains unanswered. But what stands out is that a finite universe does not necessarily have an edge, just as an infinite one is not necessarily without structure. Both of these possibilities are compatible with our current understanding. Once this idea is absorbed, it becomes simpler to release the intuitive need for a final frontier. The universe does not require an ending to be understandable. Its history, its structure, and its behavior already offer more than enough for us to explore. With the concept of edges put aside, our focus can shift to a closely related question. If the universe does not terminate at our observable horizon and might stretch far beyond it, is the total cosmos finite or infinite in its full extent? The question of whether the universe is finite or infinite is one that sounds remarkably simple but proves to be extraordinarily complex. The terms themselves are part of our everyday language, used without much thought. When applied to the cosmos as a whole, however, they take on meanings that stretch beyond their ordinary use. What lends the question its particular subtlety is that it does not just stem from simple curiosity. It arises as a natural consequence of seriously considering cosmic size, horizons, and geometry. To explore this, without getting lost in pure abstraction, it is helpful to ground the conversation in what science can actually put to the test. Cosmology does not concern itself with whether infinity feels plausible or whether a finite reality feels more reassuring. Instead, it asks what kinds of universes are consistent with our observations and with the laws of physics as we currently comprehend them. At this moment, both finite and infinite universes stand as viable possibilities. The fundamental reason this question is so challenging to resolve is tied to the limits of our own perception. Everything we know about the universe directly is sourced from within our observable region, a vast sphere with a diameter of roughly 93 billion light-years. We have no direct way to access what lies beyond that region. Any statement about the total size of the universe must, therefore, be an extrapolation rather than a direct measurement. This is not to say that such claims are merely arbitrary. In cosmology, extrapolation is a disciplined process, guided by observed patterns, the need for consistency, and established theory. But it does underscore the existence of a line between what can be empirically tested and what must, for now, remain provisional. One of the most significant clues we have comes from the study of geometry. The universe can possess different global geometries, which are determined by its total energy content. These geometries, in turn, have implications for whether the universe is finite or infinite. If space has a positive curvature, analogous to the surface of a sphere but extended into 3 dimensions, the universe would have a finite volume, yet lack any edges. In such a cosmos, you could travel in a straight line indefinitely and eventually find yourself back at your starting point. For a universe like this, infinity is not needed to account for its boundless nature. If space has 0 curvature, which is often described as being flat, then the universe could potentially be infinite, stretching out endlessly in every direction. A flat geometry does not necessitate infinity, but it allows for it quite naturally. And if space has a negative curvature, shaped more like a saddle, the universe would also be infinite, with distances between points expanding even more rapidly than in a flat space. Measurements of the cosmic geometry have revealed that space is extremely close to being flat. The margin of uncertainty in these measurements is small, but it is not 0. Within that narrow range of uncertainty, both a very large but finite universe and a truly infinite one remain consistent with all our observations. This is a crucial distinction to grasp. Apparent flatness does not automatically equate to infinity. It is possible for a universe to be both finite and flat if it possesses certain topological characteristics, such as wrapping back on itself in complex ways. While these possibilities are mathematically sound, they are exceptionally difficult to verify through observation. So, when cosmologists report that the universe appears flat, they are not making a definitive declaration that it is infinite. They are communicating that, within the region we can observe, the geometry behaves as if its curvature is incredibly small. Another clue is provided by the theory of cosmic inflation. Many models of inflation naturally lead to universes that are far, far larger than our observable region. In some scenarios, these models produce universes that are, for all practical purposes, infinite. During the inflationary epoch, space expanded at such an extraordinary rate that any initial curvature it might have had was smoothed out completely. Regions that were once infinitesimally small were stretched to astronomical proportions. If this period of inflation continued for a sufficient length of time, the resulting universe would be immeasurably larger than what we can see. irrespective of whether it is technically finite or infinite. This means that inflation weakens the link between the size we can observe and the total size of everything. Even if the universe is ultimately finite, inflation could have expanded it to such a colossal scale that we might never detect any sign of its finiteness. From a practical standpoint, a finite universe that is trillions of times larger than the observable region would behave, from our perspective, exactly like an infinite one. There would be no detectable repetition of structures, no discernible effects of curvature, and no edges anywhere within our reach. The distinction between finite and infinite, then, becomes less about the nature of reality and more about the limits of what can ever be known. There is also a common assumption that an infinite universe would necessarily imply repetition. The thinking is that if the cosmos were both infinite and uniform, then every possible arrangement of matter would likely repeat itself somewhere out in the vast expanse. The possibility exists that there are other regions of space, perfect duplicates of our own, containing copies of our galaxy, our stars, and perhaps even our entire observable universe. This concept is a recurring feature in popular scientific conversations, but it is built upon assumptions that reach beyond established knowledge. The mere presence of infinity is not enough to guarantee that such repetitions would occur. Specific additional conditions would need to be met, such as there being only a finite number of possible arrangements for matter within a set volume. It remains a subject of debate whether these conditions are actually true for our universe. And even if duplication were an inevitable consequence, it would happen at distances so immense that these regions would forever lie beyond our cosmic horizon. From the standpoint of observation, these other domains might as well be non-existent. This leads back to a persistent theme in the study of the cosmos. Cosmology makes a careful distinction between what exists and what is relevant. An object or region can certainly exist past the edge of what we can see, but have absolutely no effect on any phenomenon we can observe. From a scientific viewpoint, the debate between a finite and an infinite universe is most important for maintaining theoretical consistency. The answer shapes the way cosmological models are designed and how certain parameters within them are understood. It has no impact on our daily observations or on the arrangement of structures inside the observable cosmos. Another factor keeping this question unresolved is the inherent difficulty in detecting the universe's overall topology. If the cosmos were finite and looped back on itself, it could leave subtle imprints on the cosmic microwave background, like repeating patterns or unexpected correlations over vast distances. Scientists have diligently looked for these kinds of signatures. To date, none have been found with any certainty, but a lack of evidence is not the same as evidence of absence. The universe could indeed be finite, but with a topology so large that its repeating nature does not reveal itself within the portion we can see. There is also the challenge of cosmic variance. We have access to just a single universe, and within it, only one observable region. This situation inherently limits our statistical certainty. Some properties of the universe may simply be impossible for us to measure with precision, as there is no way to perform the experiment again from different cosmic locations. This limitation is not a failure of cosmology. Rather, it serves to define its scope. The question of finite versus infinite also intersects with our philosophical intuitions. The concept of infinity can be unsettling because it resists any sense of completion. A finite universe, by contrast, can feel more comprehensible and contained. Nature, however, does not organize itself to align with human intuition. Physics has repeatedly demonstrated that many counterintuitive concepts are, in fact, true. Time is able to stretch, space can bend, and particles can act like waves. Infinity might be another such idea, or it could be that the universe avoids it through some subtle aspect of its geometry. From a physics perspective, either possibility is valid, provided it is internally coherent and aligns with what we observe. There is an additional angle that deserves consideration. Even if the universe extends infinitely in space, it might not be infinite in every other way. It likely has a finite age. It has a finite energy density. It possesses horizons that restrict interactions. Infinity in one dimension does not necessitate infinity in all of them. By the same token, even if the universe has a finite spatial volume, it could still hold a quantity of matter and energy so enormous that it far exceeds anything we could ever hope to observe. So, the finite versus infinite question is not as simple as it first seems. It has many layers. One of these layers relates to predictability. In a finite universe, particularly one small enough for its global characteristics to be significant, the initial conditions could have a much greater influence on how things develop. In an infinite universe, local conditions might be the dominant factor, with the global structure becoming less consequential. This difference influences how cosmologists approach concepts of probability and typicality. If the cosmos is infinite, determining what constitutes a typical region becomes a more nuanced problem. If it is finite, typicality might be simpler to define, but only if the total volume is known. These are issues that are most pressing in theoretical work. For observational cosmology, the primary focus remains on what is measurable. At present, every reliable measurement we have indicates that, within the observable region, the universe seems to extend in a smooth and uniform manner. There are no indications of it wrapping back on itself, no signs of repetition, and no curvature pronounced enough to suggest a small, finite cosmos. This evidence pushes the probable scale of the universe, whether it is finite or infinite, far beyond our observational horizon. It is also important to recognize that the question of finiteness may not have a definitive answer within the framework of current physics. New theories could fundamentally alter our understanding of space, time, and geometry. Concepts, such as quantum gravity, might even change the very meaning of infinity. In this way, asking whether the universe is finite or infinite is also a method of exploring the boundaries of our current knowledge. It illuminates the point where theory and observation meet and where speculation takes over. What can be stated with confidence is that the observable universe does not demand that the greater cosmos be finite, nor does it require it to be infinite. Both outcomes are compatible with everything we have seen so far. While that may seem like an unsatisfying conclusion, it is an honest assessment of the available evidence. There is a practical lesson here as well. Despite all the discussion about infinity, the observable universe is already vast enough to defy easy comprehension. Whether or not there is more beyond its edge does not diminish the sheer scale we can already perceive. In fact, the question of finiteness can sometimes be a distraction from a more fundamental one. Given the immense size of the observable universe, how do scientists manage to measure the distances, ages, and structures within it at all? How can any of this be known with any degree of confidence? Gauging the scale of something as vast as the observable universe does not start with rulers, tape measures, or direct journeys. It starts with inference, patience, and a careful layering of methods that build upon one another. Scientists do not determine the size of the universe in one single action. They assemble a cosmic distance ladder, rung by rung, employing physical processes that can be verified locally and then extended outward with ever-increasing reach. At the most intimate scales, measurement begins close to home. Distances inside our solar system are established using geometry and timing. By bouncing radio signals off planets and recording how long they take to return, scientists can calculate distances with extraordinary precision. These measurements firmly anchor the scale of our immediate cosmic neighborhood and establish the first reliable units of measurement. Beyond the solar system, direct timing is no longer feasible, so astronomers rely on a method called parallax. As the Earth orbits the Sun, nearby stars appear to shift their position slightly against the backdrop of much more distant stars. This apparent movement is incredibly small, often less than the width of a human hair viewed from kilometers away, but it is measurable. That subtle change in position allows for a direct calculation of distances to stars up to a few thousand light-years away. The method of parallax is foundational, its strength lying in a pure geometric principle that is free from assumptions about stellar physics. It establishes a crucial first rung on the cosmic distance ladder. This technique, however, has its limitations. As we look deeper into space, the parallax angles become too minuscule to measure with any accuracy, even for our most advanced telescopes. To probe farther out, astronomers must turn to celestial objects that have a known or standard intrinsic brightness. The principle is straightforward. If you can determine how luminous an object truly is, you can calculate its distance by comparing that to how bright it appears from our vantage point on Earth, using the inverse square law of light. This law describes how an object's apparent brightness diminishes in a predictable way as its distance from an observer increases. Certain kinds of stars are exceptionally well suited for this role. There are stars whose brightness fluctuates in a very regular cycle, and the period of that cycle is directly correlated with the star's absolute luminosity. By carefully timing how quickly these pulsating stars brighten and fade, astronomers can ascertain their true brightness and, from there, their distance. These predictable stars effectively serve as standard candles. They make it possible to measure distances across immense stretches of our own galaxy, and even to neighboring galaxies. A critical detail is that nearby examples of these standard candles can be calibrated using parallax, which firmly connects this next step of the distance ladder to the first. For measuring distances beyond the local galactic neighborhood, even more luminous standard candles are required. Specific types of stellar explosions, or supernovae, are incredibly useful because they unleash colossal amounts of energy and consistently reach almost the exact same peak brightness. Their immense luminosity allows them to be observed across billions of light years. By contrasting the apparent brightness of these cataclysmic events with their known intrinsic luminosity, scientists can gauge the distances to exceptionally remote galaxies. These powerful measurements extend our cosmic distance ladder far into the observable universe. Yet, distance measurements alone are insufficient for determining the universe's total size. The expansion of the universe must also be factored in, and this is where the phenomenon of redshift becomes indispensable. When a photon of light journeys through expanding space, its wavelength gets stretched. Light that was originally blue when it was emitted can appear much redder by the time it reaches us. The degree of this stretching provides a direct measure of how much the universe has expanded over the course of the light's long voyage. Measuring a galaxy's redshift is a relatively direct process. After collecting the light from a distant galaxy, astronomers examine its spectrum, where specific spectral lines serve as unique markers, revealing precisely how much the light has been elongated. A greater redshift indicates a more distant galaxy, whose light was emitted much earlier in the universe's history. When scientists combine redshift data with distance measurements from standard candles, they can construct a detailed history of cosmic expansion. This relationship between distance and redshift is not perfectly straight across all cosmic time, as the rate of expansion has varied. Correctly accounting for these historical changes is a key part of the cosmological puzzle. The expansion history itself is a direct input for calculating the universe's size. An understanding of how quickly space has expanded at different epochs enables cosmologists to determine the present-day distance to faraway regions, even though we see them as they were when they were much closer to us. Another profoundly important tool emerges from the faint, ancient radiation that permeates all of space. This cosmic microwave background radiation is a relic from the early universe, carrying with it information from a time when the cosmos was incredibly young. Minute fluctuations in the temperature of this light correspond to sound waves that once rippled through the hot, dense plasma of the infant universe. The physical size of these primordial sound waves can be calculated from fundamental physics. By measuring their apparent size on the sky today, scientists can deduce the geometry and overall scale of the cosmos. This technique functions like a cosmic measuring rod that spans billions of light years. What makes this approach so powerful is its reliance on physical laws that have been rigorously tested in Earth-based laboratories. The very same principles that govern waves and particles here on our planet are applicable across the entire universe. This consistency allows physics on a small scale to inform measurements on the largest of scales. Large-scale galaxy surveys contribute yet another layer of data. By meticulously mapping the three-dimensional positions of millions of galaxies, researchers can detect characteristic patterns in how they are distributed throughout space. These patterns, which were imprinted by physical processes in the early universe, have a known physical size. Measuring the apparent scale of these features in the present-day cosmos provides an additional, independent method for gauging cosmic distances. It is important to note that each of these methods comes with its own set of uncertainties. No single technique provides a perfect answer. The true confidence in cosmological measurements comes from this principle of redundancy. When multiple, independent lines of evidence all point to the same conclusion, our confidence in that result grows substantially. This convergence of results is particularly vital when grappling with such extreme scales. Gauging distances across billions of light years inherently involves some extrapolation, but it is far from being a blind guess. Every step of the distance ladder is built upon the previous one, all anchored by physics that can be verified much closer to home. The element of time is also deeply intertwined with these measurements, because looking out to great distances is synonymous with looking back into the past. Scientists must therefore develop models that account for how the universe has evolved between the time light was emitted and the present day. This modeling incorporates how matter has clumped together under gravity, how the rate of expansion has changed, and how different forms of energy influence the universe's geometry. These models are not arbitrary creations. They are strictly constrained by observational data. When a model's predictions do not align with what is observed, that model must be revised or even abandoned. This iterative process has, over decades, significantly narrowed the field of possibilities and refined our measurements. One of the ongoing challenges in the field is a subtle tension that exists between different measurement techniques. Some methods produce slightly different values for the current rate of cosmic expansion. While the discrepancy is small, it has proven to be persistent. This tension does not undermine the foundations of cosmology. Instead, it points toward areas where our comprehension is still developing and where new physics may be waiting to be discovered. Even with these unresolved questions, the overall picture remains remarkably consistent. The observable universe possesses a finite and measurable size. Its vast scale is a direct consequence of its age, its expansion history, and its fundamental geometry. What is remarkable is not simply that scientists can estimate such a colossal size, but that they are able to do so with a meaningful degree of precision. The margin of error in the radius of the observable universe is incredibly small when compared to the radius itself. Achieving this level of precision would have been considered impossible just a century ago. All of these incredible measurements rest upon a single, quiet assumption that has been subjected to relentless testing. The laws of physics are the same everywhere. The behavior of light, the force of gravity, and the processes within atoms are consistent throughout the cosmos. Without this fundamental uniformity, any attempt to measure across cosmic distances would be futile. This assumption is not a philosophical preference, but an empirical finding. To date, every single observation has supported it. Consequently, when scientists state that the observable universe is approximately 93 billion light-years in diameter, this figure is not a speculative guess, but a conclusion grounded in a vast and consistent body of evidence. These figures are a summary, drawing from many overlapping measurements that are each anchored in tested physics and direct observation. That is not to suggest the number is absolute or final, as refinements will certainly continue. Various parameters may undergo slight shifts, and emerging data could adjust the overall picture. The scale itself, however, is fundamentally sound. Appreciating how this kind of measurement works also brings clarity to why the observable universe is defined as it is. It is far more than a simple concept. It is a region whose volume can be calculated, its size derived from multiple, independent lines of evidence. Long before the first stars ever ignited or galaxies began to coalesce, the cosmos produced a faint signal that continues to envelop us today. This signal is subtle, almost perfectly uniform, and very easy to miss. And yet, it holds more information about the size, age, and fundamental structure of the universe than any other single observation we can make. This ancient echo is known as the cosmic microwave background. It signifies the most distant moment in cosmic history that we are able to see directly. To truly grasp why this primordial light is so profoundly important, it is helpful to visualize the state of the universe before this light was free. In its very earliest stages, the cosmos was not transparent to light. It was an intensely hot and dense environment, filled with a sea of charged particles. Light was unable to travel any significant distance because it was perpetually interacting with matter, scattering endlessly in all directions. During this era, the universe resembled the interior of a star far more than the cold, empty space we perceive now. Photons certainly existed, but they were effectively trapped, unable to move far before colliding with electrons and other charged particles. All of space was filled with a glowing plasma, and no clear image could possibly form because light had no unobstructed path to follow. As the universe underwent its relentless expansion, it also cooled. Finally, after a period of about 380,000 years, the conditions had changed sufficiently for electrons and protons to combine, forming neutral atoms. Once this occurred, light was suddenly liberated to travel freely across space. The photons that had been held captive were released, beginning a journey through the cosmos that has been largely unimpeded ever since. That crucial moment in time is known as recombination. The light that was set free then is what we now detect as the cosmic microwave background. This light has been traveling continuously for billions of years. As the universe has expanded, the wavelengths of this light have stretched right along with the fabric of space. What originated as visible and infrared light has cooled and elongated, shifting into the microwave portion of the spectrum. Today, it reaches our instruments as a faint, ambient glow that is detectable from every direction in the sky. The cosmic microwave background does not originate from a single point or location. Instead, it comes from everywhere at once. Regardless of where one looks, one is seeing light that was emitted at the very moment the universe first became transparent, arriving from the most extreme distances we can possibly observe. This is precisely why it constitutes the ultimate observational boundary for us. Beyond this wall of light, the universe is opaque to electromagnetic radiation. There is simply no older light for us to see, because earlier photons were unable to travel without being scattered. In the context of the observable universe, the cosmic microwave background defines the most distant surface we can perceive through time. It is frequently referred to as the edge of the observable universe, but this description can be slightly misleading. It is not a physical edge located somewhere in space. It is better understood as a snapshot of the entire cosmos at a particular instant in its early evolution, seen from our unique vantage point. Because the light from that moment has been in transit for nearly the full age of the universe, the present-day distance to the regions that first emitted it is now about 46 billion light-years. This is how the cosmic microwave background helps to establish the vast scale of our observable universe. But its significance extends far beyond simply marking a distance. When scientists initially detected this background radiation, it appeared to be remarkably uniform. Its temperature was almost precisely the same in every direction, with only the most minuscule deviations. This uniformity was a monumental discovery, as it powerfully confirmed predictions made by models of an expanding universe. Those tiny variations, however small, are of critical importance. They represent minute differences in density within the very early universe. Regions that were slightly denser would eventually, over cosmic timescales, become the gravitational seeds for galaxies and clusters of galaxies. Conversely, regions that were slightly less dense would evolve into the great cosmic voids. In this sense, the cosmic microwave background provides a detailed map of the universe's initial conditions. By measuring these temperature fluctuations with extraordinary precision, scientists can extract a wealth of information about the universe's composition, its overall geometry, and its expansion history. The characteristic size of these variations, their distribution across the sky, and their statistical properties all contain encoded information about fundamental physical parameters. One of these parameters is the total energy density of the universe. Another is the precise proportion of matter, dark matter, and dark energy. A third is the curvature of space itself. What makes all of this possible is that the physics that governed the early universe is very well understood. The behavior of plasma, radiation, and sound waves within those hot, dense conditions can be modeled with great accuracy using tested physical laws. Those sound waves, rippling through the primordial plasma, left imprints in the cosmic microwave background that now serve as cosmic standard rulers. The intrinsic size of these imprints is known from physics. By measuring how large they appear to us in the sky today, scientists can calculate how much space has expanded since that distant time. This measurement directly constrains the size of the observable universe. The cosmic microwave background is therefore not merely ancient light, it is a powerful measuring instrument. What is also remarkable is its consistency. A variety of different satellites and experiments have measured it, using different instruments, different methods, and different frequencies, and they all converge on the exact same picture. They find the same average temperature, the same pattern of variations, and the same underlying statistical patterns. This internal consistency is one of the most compelling reasons that cosmologists have such strong confidence in the current model of the universe. Another vital aspect of the cosmic microwave background is that it displays no preferred direction. There is no large-scale gradient pointing toward a center or an edge. Once our own local motion through space is accounted for, the background appears identical everywhere. This observation powerfully reinforces the idea that the universe is homogeneous and isotropic on its largest scales. It supports the view that our location in the cosmos is not special, and that the observable universe is a representative sample of a much larger whole. The background also offers profound insight into the age of the universe. Through a careful analysis of its properties, scientists can calculate how much time has passed since recombination occurred. When this information is combined with our models of cosmic expansion, it leads directly to the age estimate of about 13.8 billion years. Without the cosmic microwave background, this number would be far less certain. It also provides crucial data that helps to constrain theories of cosmic inflation. The pattern of fluctuations seen in this ancient light is remarkable, as it closely matches the predictions made by inflationary models. These models describe how quantum variations in the earliest moments would be stretched to cosmic scales. While this does not prove inflation in a strict sense, it does provide incredibly strong support for the idea. This alignment is a cornerstone of modern cosmology. From the standpoint of sheer scale, the cosmic microwave background serves to unify several different threads of our story. It establishes the absolute maximum for our look-back time. It also defines the farthest observable distance from our vantage point. Encoded within its subtle variations is the geometry of the universe itself. It reflects the primordial processes that gave rise to all cosmic structure. It is, in effect, the very foundation upon which our measurements of the observable universe are built. There is also a subtle point here that deserves emphasis. The cosmic microwave background does not originate from a single, perfect, spherical shell at one fixed distance. The different regions of the background we see today actually come from slightly different distances and represent slightly different times. This variation depends on the direction we look and the local conditions in that part of the early universe. So even this oldest of all light is not a perfectly uniform snapshot in time. It has its own depth, structure, and complexity. This inherent complexity allows scientists to test the finest details of their cosmological models. Small deviations from the expected patterns can signal the presence of new physics or help to refine our existing parameters. In that sense, the cosmic microwave background is not a static relic at all. It is an active data set, continually reanalyzed as our techniques improve. Despite its immense importance, this light remains completely invisible to our human senses. We cannot see it with our eyes, nor can we feel it on our skin. It fills the room you are in right now, passing through walls, our bodies, and our instruments completely unnoticed. Its presence is only detectable with sensitive equipment specifically tuned to microwave frequencies. This profound invisibility makes its true impact easy to underestimate, and yet, it is one of the most informative signals ever measured. The existence of this background also places a hard limit on what any electromagnetic observation can ever achieve. There is simply no light older than this that can reach us. Beyond the era of recombination, the universe is observationally dark in electromagnetic terms. This does not mean that nothing existed in those earlier times, only that information from that epoch is inaccessible through the medium of light. Other messengers, such as gravitational waves, may one day carry information from these earlier times, but for now, those signals remain incredibly challenging to detect. Thus, the CMB marks a fundamental boundary. So, in a very literal sense, the cosmic microwave background marks the beginning of observational cosmology. It is the moment the universe first became visible. Everything else we see, from galaxies to stars and quasars, appeared later in cosmic history. They are all layered on top of this ancient backdrop. From a scale perspective, the background reinforces the idea that the observable universe is not arbitrary in its size. Its dimensions are tied directly to physical events in the early universe. The distance to this background is not a guess, but a figure calculated from known physical processes. That calculated distance, when combined with cosmic expansion, defines the observable horizon. It is a horizon in time as much as in space. Another interesting consequence is that the observable universe grows older, but not necessarily larger in the way our intuition might expect. As time passes, we do continue to receive light from regions slightly closer to the time of recombination. However, The accelerating expansion of space puts a limit on how much farther this horizon can actually extend. Therefore, the cosmic microwave background will always represent the earliest visible moment, even as the universe continues to age. This gives the observable universe a kind of built-in ceiling. No matter how long we wait, there will always be a time before which light simply cannot reach us. That ceiling shapes everything we can possibly know about the cosmos. At the same time, the background provides a profound sense of unity. No matter where you were in the universe, if you could observe deeply enough, you would see a similar background surrounding you, marking the very same early epoch and reinforcing the idea that the universe is governed by universal laws. As this picture settles, it becomes clear why the cosmic microwave background is so indispensable. Without it, the size, age, and structure of the observable universe would be far more uncertain, but with its discovery, those properties become measurable. So if this oldest light sets the ultimate boundary, and everything we see is layered between it and the present, a question emerges. How does a human mind make sense of such a scale without losing its orientation? This shift often happens quietly, almost without notice. After hearing numbers large enough to fill pages with zeros and tracing structures that stretch for hundreds of millions of light years, something inside the mind stops reacting the way it used to. The universe does not keep feeling bigger. Instead, it can start to feel strangely small. This is not because it is actually shrinking. It is because the human mind has reached the edge of how it processes scale. This response is not a failure of understanding, but simply a feature of our cognition. Human perception evolved to handle distances measured in steps, minutes, or days of travel. Our brains are very good at comparing the size of a tree to a house, or a hill to a mountain. Even continents and oceans can be grasped indirectly because they connect to our lived experience. Cosmic scale does not connect in that same way, arriving only through language, numbers, and abstraction. When someone hears that the observable universe is about 93 billion light-years across, the number itself is registered correctly, but the meaning does not grow proportionally. After a certain point, adding more zeros does not make something feel larger. It simply moves the concept into a category labeled very big, where distinctions begin to blur. This is why, paradoxically, the universe can begin to feel conceptually smaller as its measured size increases. Once it exceeds our intuitive scale, it becomes a single mental object. A galaxy, a cluster, and the observable universe can start to feel like variations on the same idea, not radically different scales. Psychologists sometimes describe this as scale saturation. Beyond a certain magnitude, the brain stops tracking proportional differences. The numbers 10 million and 10 billion no longer feel distinct in the way that 10 and 100 do, as they are understood symbolically, but not experientially. This effect helps to explain why cosmic discussions can feel oddly calming rather than overwhelming. Once the universe passes beyond the range where the mind tries to map it onto physical experience, it stops triggering stress responses. There is nothing to brace against. The scale becomes distant in a literal, cognitive sense. In this way, the vastness of the universe does not press inward, it recedes. A related effect also involves our internal points of reference. In our daily experience, we comprehend size through the act of comparison. A car is understood as large when placed next to a bicycle. A city is considered vast when contrasted with a small town. When we turn to cosmology, however, these familiar points of reference simply dissolve. The observable universe is not merely larger than the objects we know. It is so immense that it transcends comparison itself. Without these anchors, the human mind instinctively adapts by condensing this scale. The entire cosmos becomes a singular object, a concept with a label, rather than a space that must be mentally traversed. This process of compression can make the observable universe feel surprisingly manageable. Once it is conceived as a sphere with a specific, albeit staggering, diameter, it gains conceptual boundaries, even if none exist in physical reality. An entity that is infinite or indefinite is far more difficult to hold in the mind than one that is finite, even if it is enormous. Therefore, learning that the observable universe possesses a measurable diameter can paradoxically make it feel smaller than an endless, unknown void would. The very act of measuring extreme phenomena creates a sense of containment within our thoughts. Another element that shapes our perception is the familiarity that comes with repetition. An initial encounter with cosmic scales can be quite shocking. Hearing for the first time about billions of years or trillions of stars often inspires a profound sense of awe or even unease. Yet over time, repeated exposure to these figures makes them feel normal. They transition into background information instead of remaining active sources of surprise. This normalization does not imply that the universe has actually become any less vast. It simply means our minds have grown accustomed to the idea. The very same process can be observed in other fields. Individuals who work with massive data sets eventually stop having an emotional reaction to large numbers. Astronomers routinely talk about distances that would overwhelm our intuition if we were to encounter them for the first time. Familiarity cultivates a sense of calm, not because the scale has diminished, but because it is no longer a novelty. There is also a linguistic component at play here. Words such as galaxy, cluster, and universe serve as conceptual containers. They permit incredibly complex structures to be compressed into single, simple terms. Once these structures are packaged in this way, they become much easier to handle mentally, even though their contents remain immeasurably vast. In this sense, language functions as a kind of cognitive tool, pulling sprawling concepts into more manageable shapes. This is not a form of deception, it is a matter of efficiency. An additional reason cosmic scale can feel smaller than one might expect is that it makes no demands for action. In the everyday world, vastness often implies a need for effort. A great distance is something that must be crossed. A massive object is something that must be moved or navigated around. The scale of the cosmos presents no such requirement. There is nothing for us to lift, no journey to undertake, and nothing from which to escape. The universe does not ask for a response from us. It simply is. In the absence of a call to action, the emotional intensity of its scale begins to soften. The mind is free to observe rather than compelled to react. This sense of detachment is further reinforced by the reality that cosmic scale has no direct bearing on our daily lives. Whether the observable universe spans 80 or 100 billion light-years across has no effect on how gravity works on Earth or how time unfolds within a room. The scale remains intellectually profound but practically inert. Because of this, the size of the universe can be contemplated without setting off feelings of urgency or fear. It is immense, but it is not pressing. A deeper psychological pattern is also involved. Human beings naturally place their own experience at the center of everything. This is not a sign of arrogance. It is simply the way perception is structured. All information is filtered through a single point of individual awareness. When cosmology reveals that every observer is situated at the center of their own observable universe, it unintentionally resonates with this deep-seated instinct. The universe feels as if it is centered around us, not because it truly is, but because that is how the act of observation is framed. This alignment helps to reduce cognitive dissonance. The cosmos may be vast, but its observable structure feels familiar to our mode of perception. In contrast, a universe with a single, visible center, located somewhere else, might feel far more disorienting. The lack of any preferred central point allows the mind to comfortably settle into its own frame of reference without conflict. Another subtle influence arises from the dimension of time. Cosmic scales play out over billions of years. Human experience, on the other hand, unfolds over seconds, minutes, and decades. When timescales are separated by so many orders of magnitude, the mind sorts them into entirely different categories. Cosmic time becomes an abstract concept, no longer in competition with the time we personally experience. This separation effectively reduces emotional interference. Events that took place billions of years in the past or will occur in the distant future feel insulated from our immediate concerns. The universe becomes an object of thought, not a situation that needs to be managed. This insulation can foster a gentle distance, which makes cosmic ideas well suited for reflection rather than reaction. Scale becomes a source of contemplation instead of alarm. There is also a paradox here that is worth noting. While the scale of the cosmos can make our individual concerns seem small, it does not necessarily strip them of their importance. The mind is fully capable of holding multiple scales of meaning at the same time. A small, personal experience can retain its significance even when set against an immense backdrop. In fact, this very contrast can serve to enhance meaning rather than to erase it. The knowledge that the universe is vast does not negate our local experience. It simply contextualizes it. This is why people often describe a feeling of calm when they think about the universe at large. Problems that feel overwhelming on a personal level can loosen their grip when they are placed within a much broader context. This is not because they are unimportant, but because they are no longer seen in isolation. Cosmic scale offers perspective without passing judgment. An interesting asymmetry also exists in how we perceive size. Extremely small scales, like those of subatomic particles, can feel more unsettling than extremely large ones. The notion that reality is constructed from components far beyond our sensory reach can provoke a sense of discomfort. The largeness of the universe, by contrast, often feels open and expansive rather than intrusive. This may be because large scales remain external to us. Small scales, however, feel as if they are undermining reality from within. So, the observable universe, in spite of its size, does not threaten the coherence of our experience. It expands outward instead of dissolving inward. Another element that shapes our perception is the smoothness of cosmic laws. The same fundamental principles of physics apply consistently across the entire observable universe. There is no chaos at the largest scales. The expansion of space is orderly. The formation of structure follows predictable patterns. This underlying regularity provides a sense of cognitive stability. If the universe were both vast and lawless, its scale might feel terrifying. Instead, it is vast and highly structured. This structure allows the mind to be at ease. There is no need to keep track of infinite variations. Patterns repeat themselves, statistics are applicable, predictability exists. Even the fact that most of the universe is empty space contributes to this feeling of calm. Emptiness inherently reduces any sense of perceived threat. The observable universe is not a crowded, pressing environment. The cosmos is defined by its sparseness, where islands of matter exist across immense separations. This very quality of spaciousness mirrors a profound quiet. It seems to invite contemplation more than it does alarm. There is also a narrative element at work in our understanding. The field of cosmology frames the universe as a story that develops through time, moving from a state of simplicity toward one of complexity. Stories are often more readily absorbed than static, immeasurable concepts. The universe, in this telling, becomes a sequence of events rather than a single, monolithic entity. When immense scale is woven into a narrative, it becomes more approachable. The human mind can track a process of change with greater ease than it can grasp a fixed and infinite state. So, the observable universe can feel smaller, not due to its actual size, but because of the way it is explained. This act of explanation helps to tame the scale. Another factor that makes the scale feel less overwhelming is cosmology's frequent emphasis on the boundaries of our knowledge. The observable universe is, by definition, limited. It has horizons. There are regions we are unable to see. An intriguing paradox emerges here. Knowing that such limits exist actually lessens the conceptual burden. A truly unlimited cosmos, one without any observational frontiers, would be far more difficult to mentally contain. A universe that possesses a defined, observable area provides a sense of closure, even if that closure is incomplete. This horizon gives a definite shape to our ignorance. It effectively states that this is the portion that can be known directly. Such clarity has a calming effect. A certain emotional resonance can also be found in the knowledge that every observer possesses their own unique observable universe. This implies that no single perspective is excluded from the cosmic tapestry. Regardless of your location, the universe unfolds around you in the same essential manner. This shared universality fosters a feeling of belonging rather than one of insignificance. The mind reacts very differently to being a small part of a vast system compared to being an irrelevant part of one. Cosmology points toward the former, not the latter. We may be small in physical scale, but we are not incidental. This is a crucial distinction. As these psychological layers build up, the observable universe transforms into something that can be held gently within one's thoughts. Its sheer size does not need to be fought or conquered. It can simply be acknowledged. And that acknowledgement more often brings a sense of stillness than one of agitation. There is a clear reason why contemplating the universe late at night feels distinct from considering it in the midst of a busy day. As our attention slows, the cosmic scale ceases to compete with our immediate concerns. It shifts from the foreground into the background. In that quieter state, the universe no longer feels like a challenge to be solved. It feels like context, and context is something that does not require a resolution. Gaining insight into how the human mind processes cosmic scale does not detract from the science itself. In a way, it completes it. Measurement can tell us the size of the observable universe. Psychology can tell us how we live with that information. When brought together, they help explain why something so extraordinarily large can feel so deeply quiet. Somewhere between the greatest numbers we are capable of naming and the tranquil moment you find yourself in now, the observable universe goes on doing what it has always done. Space continues to stretch, light continues to travel, and time continues to advance, never asking for our notice. And while no part of that process is dependent on our attention, there is something distinctly human in the act of pausing to notice it all the same. At this point, the concept of the observable universe might no longer seem so sharp or imposing. It may feel more rounded, more settled, almost familiar, despite its vastness. This isn't because it has shrunk, but because it has been traced with care, layer by layer, without any rush toward a final conclusion or an attempt to force it into a single image. The observable universe is enormous, but it is also specific. It possesses a size that is subject to calculation. It has a history that is open to reconstruction. It has boundaries that can be described without suggesting a final end. This region is not all of existence, nor does it need to be. That difference matters more than one might initially think. What we refer to as the observable universe is not a declaration about ultimate reality. It is a statement about our connection to it. It delineates the part of the cosmos that has had enough time to interact with us through the language of light and physics. It is the portion of everything that has, in a very real sense, reached out and made contact. Everything contained within it is bound by a shared history. The light now arriving from faraway galaxies began its journey billions of years ago, traversed expanding space, and finally reached us, carrying with it information about how the universe used to be. That link is delicate, delayed, and far from complete, but it is undeniably real. Beyond that observable horizon, reality almost certainly continues. Space does not just become empty. Time does not cease to flow. The universe does not terminate simply because our view of it does. What ends is our capacity to receive its signals, to collect evidence, and to confirm things directly. This limitation is not a failure of our curiosity or our technology. It is a fundamental feature of the way the universe operates. The horizon is a consequence of the universe having a finite age and information having a finite speed. These two facts, working together, define the entirety of what we can ever witness. They are what give the observable universe its shape. And that shape is not a static one. As time moves forward, the observable universe itself changes. Light keeps arriving from areas that were previously beyond our reach. Simultaneously, the accelerating expansion of space means that some regions we can see today will eventually fade from view. Their future signals will be stretched out beyond any hope of recovery. The observable universe, therefore, is not a fixed container. It is a living boundary, one that is perpetually renegotiated by cosmic expansion and the flow of time. This makes it less like a box and more like a shoreline. The water is always moving, the horizon is always shifting, but the land beneath it all remains. To stand at such a boundary can feel paradoxical. On the one hand, it serves to underscore our limitations. There are things we are destined never to see. On the other hand, it highlights an incredible abundance. Even within these confines, the observable universe holds more structure, more history, and more scale than our intuition can ever fully absorb. There are hundreds of billions of galaxies inside this region. There are trillions upon trillions of stars, immense webs of matter sculpted by gravity, an ancient light that carries the echoes of the universe's first moments. And yet, none of that immense reality imposes itself on the present moment. Right now, wherever you may be, the observable universe includes you, but it demands nothing in return. It does not require your comprehension in order to continue its existence. It does not need to be visualized with perfect accuracy to remain vast. The universe does not quiz us on our understanding of it. It simply is. This realization can offer a quiet sense of relief. The scale of the cosmos does not impose a responsibility. It provides a context. You are not required to hold the entire universe in your mind. You are permitted to let it be large without feeling the need to master it. In fact, one of the most genuine responses to the cosmic scale is to cease reaching outward and instead allow that perspective to settle inward. When attention returns to the present, the universe does not diminish in size. Instead, it becomes more deeply integrated. The very same physics that directs the expansion of space also presides over the atoms in the room around you, and the fundamental laws that sculpted the galaxies also assembled the elements that constitute your body. There is no rigid separation between the cosmic and the local, only a difference in scale, and scale itself does nothing to reduce relevance. The observable universe may stretch nearly 93 billion light-years from one edge to the other, but this staggering fact does not make the moment you are now experiencing any less significant. It simply exists on a different axis of reality, not a lesser one. Cosmology is often described as a humbling field of study, and it is, though not because it renders everything insignificant. Its power to humble lies in its revelation of continuity. The same cosmos that holds unimaginable distances is also the one that contains quiet rooms, the slowing of breath, and periods of deep reflection. These two realities are not in competition with each other. If anything, the sheer magnitude of the observable universe makes the existence of a calm moment all the more remarkable. There is also a profound reassurance in knowing that no matter how far outward our gaze extends, the universe continues to be governed by the same consistent rules. It does not descend into chaos at immense scales, nor does it abandon its inherent structure or dissolve into unpredictability. Expansion follows precise equations, light travels along defined paths, and matter responds to gravity. Across it all, patterns repeat. This underlying regularity allows curiosity to be at ease. There is no urgent imperative to solve every mystery at once. The universe has been unfolding for billions of years and is not waiting for our conclusions. In this sense, the observable universe invites a different kind of relationship with knowledge, one of continued observation rather than conquest or completion. The horizon will always be present. The boundary of what we can see will always exist. And this is not a flaw in the cosmos, but rather the very condition that gives observation its meaning. Without limits, there could be no structure to what we know, and without horizons, there could be no perspective. To contemplate the edge of the observable universe, then, is not to stand at the brink of an ending. It is to acknowledge the place where direct connection fades into inference, and where evidence gives way to the realm of possibility. And a possibility does not need to be resolved to be meaningful. Beyond that distant horizon, the universe likely continues on in much the same way it does here, with more space, more matter, and more time. But none of that needs to be settled tonight. What can be settled is the idea that the observable universe is not an obstacle to comprehension. It is an invitation to slow thinking, to a form of curiosity free from pressure, and to a perspective without urgency. You are allowed to let the immense numbers soften into the background. You are allowed to cease the effort of visualizing such distances. You are allowed to let the universe remain vast without forcing it into perfect clarity. Science does not demand constant engagement. It benefits greatly from rest. And this rest is not a form of disengagement. It is the act of allowing ideas to settle into a background awareness, where they can exist without being actively processed. Right now, the observable universe includes every place from which light has had time to reach us since the cosmos first became transparent. It includes ancient radiation still passing silently through the void, and galaxies whose light began its journey long before Earth existed. It also includes this present moment, not because this moment is cosmically special, but because all observation must begin from here. This fact does not elevate or diminish anything. It simply connects, and that connection is enough. So, as your attention eases and thoughts begin to drift, the universe does not need to be held tightly in the mind. It can remain vast, structured, and quietly ongoing, whether or not it is being actively considered. The edge of the observable universe is not a precipice to stand upon. It is something to be aware of gently, without expectation. There will always be more to learn, always be unanswered questions, and always be regions beyond our reach. None of that prevents the understanding we do have from being meaningful right where it is. For now, it is enough to know that the universe is large, but not infinite to your experience, that it is bounded by time, not by walls, and that it continues beyond what can be seen without needing to be imagined with precision. And wherever you are, the observable universe unfolds around you in the only way it ever can, centered on your unique position in space and time. This is not because you are central to the cosmos, but because the act of observation itself is inherently central. Nothing needs to conclude here. The universe will continue to expand, light will continue to travel, the horizons will remain where they are, and curiosity can rest, knowing that even at the very edge of what can be seen, there is no pressure to go any further tonight.